Um, so, so I'm going to, so post lunch session, I know how difficult it is to listen after post lunch session. But Niva, I'm going to give brief inputs regarding the optimal filtering techniques for communication applications and AI-driven signal processing as part of this FDP. Um, Madam, shall I share the screen?
Yes, ma'am.
Madam, is it visible?
Yes, ma'am. It is visible, ma'am.
So, I'm going to address some of the important topics regarding the optimal filtering techniques for communication applications and AI-driven signal processing techniques. So, we know that in today's fast evolving communication
Yes,
landscape,
madam.
the demand for
Yes,
am I audible?
yes, ma'am. It is audible. Ma'am, kindly keep it in slideshow mode, madam.
Okay. Is it okay now?
Yes, madam. It is fine.
Right. Right. Today, the demand for reliable, efficient, and non-noise resilience data transmission is ever increasing. So we are all know about this one. So optimal filtering basically plays a crucial role in ensuring the accuracy and integrity of signals, especially in environments affected by the noise distortion as well as the interference. So I'm going to focus on some of the important concepts which are relevant to the optimal filter design and analysis, which focuses on practical applications in communications, which includes some of the important mathematical approaches like estimation theory, adaptive filtering, and Kalman filtering. And also, I'm going to address AI-driven signal processing techniques in this particular session. So we know that signal processing is a field of engineering, mathematics, and computer science, which basically deals with processing, analysis, and manipulating analog as well as the digital signals. So the signals can be audio signals or video signals or sensor data, images, and many other types of data which are being available. So signal processing techniques are used in a wide range of applications. So can you give some applications of signal processing participants? So these are the some of the applications of signal processing, especially in the telecommunication. So what is the role of signal processing in telecommunication? Can anyone? Hello? Yeah, me audible?
Yes, ma'am. It is audible, ma'am.
Okay, okay then. So in telecommunication, signal processing techniques are used in telecommunications. So we all aware of this one to transmit the data and receive the data and process the signals over communication channels, isn't it? So this basically includes tasks like modulation, demodulation, error correction, and signal amplification, and all these things are basically comes under the telecommunication, where the signal processing plays a very important role. And the next one is the audio and video processing. So in this one, signal processing techniques are used to enhance the quality and clarity of audio as well as the video signals, as well as to extract the features like speech, music, and moving objects, and so on. And in image processing, these techniques, signal processing techniques are used to improve the quality and resolution of images, as well as to extract the features like edges, shapes, and also textures, and so on. And speech recognition in so these are signal processing techniques are used to analyze and interpret speech signals, enabling the development of systems that can transcribe speech or recognize spoken commands, and also in the control systems. So these signal processing techniques are used in control systems to stabilize and optimize performance of systems by processing feedback signals from sensor data or actuators. And also, a very important thing is biomedical engineering. So, where the signal processing techniques are used in biomedical engineering in order to analyze and interpret signals from medical devices like electrocardiograms, ECGs, and magnetic resonance imaging, MRI scanners, and so on. So not only like sciences and engineering application, but also it has applications in financial engineering. So these are used in financial engineering to analyze and interpret financial data and to develop predictive models for financial markets. So there are many applications of these signal processing. So in modern communication systems, basically operate in highly challenging environments filled with noise, interference, and channel impairments. So some of the key issues include like thermal noise, multipath fading, interference from other users, and nonlinear distortions, which are introduced by the channel or devices. So in order to extract the original information reliably, we apply signal processing techniques. So especially for filtering the noise. So optimal filtering is the process of excuse me, designing filters that give the best possible estimate of the desired signal. So in most cases, we optimize by minimizing the mean square error. So that is the ultimate goal of this optimum filtering. And in recent years, basically, AI-driven signal processing has emerged as a major advancement. So making systems more intelligent as well as adaptive, especially in technologies like 5G, beyond 5G, like 6G, IoT, and cognitive radio, and so on. So, how this signal processing works is another important thing. So, signal processing involve the representation, manipulation, and analysis of analog as well as the digital signals, right? So, the steps involved can vary depending on the specific application and also the goals of the signal processing systems. So, here the signal processing. So, these are the different steps. You can see the different steps of signal processing, how a signal processing works, like signal acquisition, conversion, representation, manipulation, analysis, synthesis, and output. So signal acquisition, this is actually the first step in signal processing. So this is to acquire the input signal. So this may involve using sensors to measure physical quantities like temperature or pressure or accelerator, or it may involve capturing audio, video, or other types of data even. And second one is the signal conversion. So once you acquire the data, then this input signal is an analog format. Analog format. So it may need to be converted into digital format. So how can we convert analog data into digital data, participants? Conversion. How can we do conversion analog format into digital format? By using analog to digital converters, right? So this allows the signal to processed using digital techniques like mathematical operations and algorithms. And after this one, the signal has to be represented. That is, the input signal is then represented in a suitable form for processing. This may involve representing the signal as a discrete sequence of samples or as a continuous function. And now the signal manipulation. So the input signal is then manipulated using various techniques like filtering or noise reduction, compression, feature extraction, and so on. So these techniques can be implemented using algorithms and mathematical operations. And another important thing is the signal analysis. This is one of the most important processing step in the signal processing. So the analysis means that the manipulated signal is then analyzed in order to extract useful information or to make certain decisions. So this may involve like detecting patterns or features in the signal, or classifying the signal into different categories, or estimating the values of certain parameters. So this signal analysis tells what a signal is trying to tell you. So it gives what actually the signal is trying to tell you. So it is the process of examining, interpreting, and understanding signals to extract useful information from them. And signal synthesis is another important thing. So here The output of the signal processing system may be synthesized signal, so which is generated based on processed input signal and any additional information or constraints. So that means it is about building or generating a signal from scratch, often based on certain specifications. So that is I think the difference between signal analysis and signal synthesis. Signal analysis is what a signal is trying to tell you, is a signal analysis. So extracting information, useful information from the signal is signal analysis. And signal synthesis is it is building or generating a signal from giving certain specifications. That is creating or generating signals artificially using some mathematical models or algorithms or electronic circuits. So and then the signal output. So the final step in signal processing is to output the resulting signal. So this may involve converting the signal back to the analog format using digital to analog converters or displaying the signal on screen or speakers. So these are the signal processing stages actually. Now, another important thing is the different signal processing techniques. So, how to achieve the signal processing? So, we will have many techniques used in signal processing like filtering, Fourier analysis, noise reduction, compression, modulation, and demodulation. We are familiar with all these different techniques. Filtering is it involves removing unwanted frequency components, right? And Fourier analysis, this is a method for representing signal as a sum of sinusoidal functions. So any signal can be represented as a sum of sinusoidal functions. It is used to identify the frequency components of signal and to analyze its properties. And noise reduction. So this is another important signal processing technique which involves removing or reducing the unwanted noise because when we are dealing with the communication, so the bottleneck for the performance of any communication system is the noise. So signal processing, by using different signal processing techniques, we can avoid the noise, remove the noise. So techniques for noise reduction includes like filtering or averaging and use of noise cancellation algorithms and compression. So in order to reduce the redundancy, the compression strategies are normally being used, which is one of the most important signal processing technique. So it involves reducing the size. So size reduction by reducing the redundancy, so which reduces the redundancy. And compression is often used to reduce the size of audio and video files for better storage or transmission purposes. And modulation, demodulation, we are familiar with these two tasks. So the modulation, which involves encoding information onto a carrier signal for transmission or communication channel. So we know that many modulation techniques are available, like amplitude modulation, frequency modulation, phase modulation, and so on. And demodulation, the reverse process. Demodulation is the reverse process of modulation, that is extracting the original information from the modulated signal. So these are the different signal processing techniques, and in order to use these different signal processing techniques, we normally have the different algorithms. We'll use different signal processing algorithms like convolution, fast Fourier transforms, correlation, adaptive filtering, Kalman filtering, Wheeler transformation, compression algorithms like this. So convolution, so this is an algorithm that is used to perform filtering, prediction, and smoothing of signals. So convolution can be used to implement a wide range of filters, including low pass, high pass, and band stop filters. Fast Fourier transforms. So this is an efficient algorithm for computing the discrete Fourier transforms of a signal. Discrete Fourier transform of a signal. So it is basically used for spectral analysis. Fast Fourier transform is used for the spectral analysis and for evaluating the frequency content of the signal. The Fourier transform decomposes a signal into its constant frequency components, so which can be used to analyze as well as modify the signal. And correlation, so this is an algorithm that is used to measure the similarity between two signals, how similar they are. So it is often used for pattern recognition and for finding the delay between two signals and at each time point, and also computing similarity score based on the degree of overlap and all these things. And adaptive filtering, this is a class of algorithms that can adapt adapt to changing signals or environments. So they'll take the current traffic also into account accordingly they'll perform. So they're often used for noise reduction and for equalizing channels in communication systems. So these adaptive filtering is another important aspect in signal processing algorithms. So these adaptive filters adjust their responses based on the input signal, allowing them to adapt to changing conditions. And then carbon filtering is another important one. So which is an optimal filtering technique. So this is an algorithm used to estimate the states of dynamic system from noisy measurements. So I'm going to concentrate a bit on Kalman filtering also in this session. So this Kalman filter is widely used for the tracking applications and prediction in a variety of applications. So it uses a model of system to predict the future state and then updates this prediction based on the measured data. And similarly, wavelet transformation. So this is an algorithm that is used to represent signals in terms of wavelets. So which are functions with localized frequency content. So it is often used for denoising and for analyzing signals with time varying frequency contents. And compression algorithms. So these algorithms are used to reduce the size of digital signals by removing redundant or unnecessary information. Participant, can you name some of the compression algorithms that we are using in communications? Anyone? Have you ever heard about Huffman coding, Shannon Fano coding? So there are some of the compression algorithms in order to reduce the size of the information so that the effective utilization of bandwidth is possible. Now, so we have seen the different the processes are the different steps of signal processing and different processing techniques and also different processing algorithms. So in order to implement all these things, we have the different tools. So different tools are normally being used in order to perform all these different algorithms. So we are familiar with the MATLAB. So MATLAB is used for the signal analysis and also filter design, simulations, and also for teaching as well as the research we are using today. We are using MATLAB. And Python, so in Python, we can do the DSP coding, FFT analysis, and audio, video, image processing applications. So we can do it in Python programming. And Octave is another important thing. So it is a free alternative to MATLAB for DSP simulations and teaching purpose. And Scilab, so Scilab, it is for signal processing and control systems and also for the academic purpose, we can use the Scilab. LabVIEW, so this is a real-time data acquisition, industrial signal monitoring instrumentation. We can use LabVIEW. And we have the another one, GNE radio. So this is especially used for wireless communication or software-defined radio. So GNU is a recursive acronym. GNU is not Unix radio. So it is an open source software toolkit which is used for the SDR. This is used for SDR and signal processing and communication system development. So Simulink, you're familiar with this one, block-based DSB modeling. So we have MATLAB Simulink also and real-time simulation with hardware and Xilinx Vivado Intel. So FPGA-based high-speed DSP implementation can be done with this. And Quartus, this is another one. And Code Composite Studio. So for programming DSP processors for real-time embedded DSP and Audacity, and this is audio signal editing, noise removal, spectral analysis. So see how many different tools are available. So we can make use of all these tools in order to perform the signal processing algorithms. Now, if you see all these things, we have different challenges with these signal processing. So there are several challenges that can arise in signal processing. So which basically includes this noise and interference, bandwidth, limited bandwidth, non-linearity, time varying systems, limited data. Noise and interference, because the signals often contains unwanted noise or interference, right? So that can distort the information being transmitted, and removing or reducing this noise can be challenging, especially if the characteristics of the noise are not known. And also the system may be stationary system or non-stationary system. So identifying and removing or reducing this noise is ultimately a challenging task. And limited bandwidth, so bandwidth of communication channel is the range of frequencies over which it can transmit the signals, right? So if the bandwidth is limited, it can be difficult to transmit a signal with a wide frequency range or high data rates. And non-linearity, since many systems, particularly those involving analog signals, which exhibits non-linear behavior, so which can make them difficult to analyze and model. So nonlinear system can exhibit complex behavior like oscillations or bifurcations, so which can be difficult to predict. And time varying systems is another challenging task, because many signals and systems change over time, so they are not stationary. So and modeling and analyzing these time varying systems can be challenging. Time varying systems may require the use of time domain or frequency domain techniques, or a combination of both in sometimes. And limited data, see, in some cases, what happens is the available data for signal or system may be limited. So, either in terms of the amount of data or the range of conditions under which it was collected. So, this can make it difficult to accurately model or analyze the system. So, these are the challenging challenges that can be faced during this signal processing. So, so here, so signal processing fundamentally deals with extracting useful information from signals, so that are often corrupted, uncertain, incomplete sometimes, or dynamic. So these difficulties directly motivate the use of optimum filtering, and estimation theory, and so on. So since to recover the original signal as accurately as possible, we need a filter, obviously, so that minimizes some error criteria. So optimum filtering is which refers to the design of filters that produces the best possible estimate of the desired signal from a noisy or distorted observations. So we also have adaptive filters, right? So that adjust their coefficients automatically, and optimal filters like Wiener and Kalman filters. So we evaluate filter performance using metrics, especially mean square error or improvement in signal to noise ratio and reduction in bit error rate, so on. So overall, filtering is crucial in many of the applications, communication applications. Suppose if you consider modulation or demodulation, equalization or channel estimation, and so on. So optimum filtering aims to find the filter that gives the best estimate of the desired signal from noisy observation in the presence of noise. So the optimization problem is to minimize the expected value of the squared error between the desired signal d of n and the filtered output y of n. So this results in filter coefficient that produces the minimum possible estimation error. So there exist two optimum filters which are widely being used, are Wiener filters and Kalman filter. Wiener filter and Kalman filter. So as we have discussed, the communication system mainly deals with the noise fading, interference, multipath distortion, and all, where the optimal filters improves the signal clarity and reduce bit error rate, enhance receiver sensitivity, channel estimation, reliable data recovery. So they ensure the system performs at its theoretical best under given constraints. So these Wiener filter and Kalman filter are the two major optimum filters. So Wiener filter handles stationary environments where the signal and noise statistics do not change. So stationary environments, static environments here. Whereas the Kalman filter handles time varying environments using a state space approach. So both have become essential in communication receivers, especially for the noise reduction. So and also used in noise reduction systems and many tracking applications. So this Wiener filter is a classic optimum filter. It is a linear and minimum mean square error filter used when the signal and noise both are stationary. So it relies on autocorrelation and cross correlation functions to compute the filter coefficients. So the solution is given by Wiener of equations, which provides a closed form optimum answer. And we use Wiener filters in noise reduction, especially in speech processing, image deblurring, channel equalization, and echo suppression, and so on. And its advantages are it is simple. So Wiener filter is simple and it offers a mathematically optimal solution. But it works under the stationary conditions. So it requires accurate knowledge of statistical characteristics and does not work well for the non-stationary environments. So Kalman filter, it is suitable for the non stationary environments. So it extends optimal filtering to dynamic time varying environments. And it basically uses the recursive prediction and correction structure. So recursive prediction correction structure it is. So it basically comprises with the two important stages or steps, prediction step and correction step. So prediction step, we estimate the next state of the system, and correction step, the estimate is updated using the incoming noisy and measurement. And Kalman filter is a powerful tool actually. So because it gives a minimum mean square error estimate in real time and adapts to system variations even. So we have different real-time applications for the Kalman filter like GPS, INS navigation systems, 5G massive MIMO channel estimation, radar tracking, robotics. So and also even in the sensor fusions are for IoT. So many applications are there. But still it has got some limitations. It includes the need for accurate mathematical modeling and also Gaussian noise assumptions and increased computational complexity compared to the Wiener filters. So these are these two are some of the important things. And optimum filtering aims to minimize the estimation error, and the Kalman filtering is the optimum filter for time varying state based systems, and it provides the best estimate of system states using the recursive algorithm. So, which basically forms the backbone of an important theory, which is known as the estimation theory. So, many applications in science and engineering require estimation of the states of a system that changes over time using sequence of noisy measurement made on that particular system. So, estimation theory is since Kalman filter means it is an estimator. So it is going to find the future behavior of any dynamic system. So the backbone for this one is it forms the backbone for state estimation theory. So it has been a fundamental tool. A state estimation theory is the fundamental tool in fields like communication, signal processing, ocean and space research, and biomedical engineering, and many problems in science and in engineering requires since estimation of the states of system that change over time. Uh, as we mentioned that using a sequence of noisy measurements made on that particular system. So state estimation is one of the best mathematical approaches. So, in order to aim, it basically aims to analyze the variance in the states of the system or process. So, and it is employed to produce the best estimate of the true state of the system. So, estimator is a tool that predicts the future behavior of a model from the available information. So, based on the available information, it is going to predict the future behavior of a model. The modeling and performance analysis. So, performance analysis means it is completely based on the simulation results of various nonlinear estimators. It is carried out here. So, system models of various nonlinear estimators and applications of these estimators for different real-time applications and their performance analysis in terms of speed of convergence or error performance and all these things. And the state estimator concerns the problem of estimating the probability density function for the state of a process which is not directly observable. So this involves both predicting the next state and applying the corrections based on the measurement equations. So here actually the two important things in state estimation is state as well as the estimator. State means the state of a system gives the complete internal condition of the system at any given instant of time and is represented mathematically by a numerical vector. So suppose, for example, let us consider an electric motor. So this is a system. So this is a system. What are the states of electrical motor participants? Anyone? What are the states of electric motor? So which basically includes the states of the electric motor basically includes the current through the windings or position or speed of the motor shafts, etc. So for our engineering applications, suppose for an orbiting satellite, the present position of the satellite, present position means which basically requires a range, azimuth as well as the elevation, right? And velocity, acceleration. So these may be the states. And the states of underwater vehicle, if you consider, so that may be their range, speed, bearing, course. So these comes under the states of the system. So even for biological system, the blood sugar levels or heart and respiration rates becomes the states. So if you see in all these examples, the states of each system gives the complete internal behavior of the system. So therefore, the field of estimation theory can virtually apply to any field of science as well as engineering. Okay. So the estimation of states for engineers are important for two reasons. So the first one is to implement state feedback controller. So for example, suppose if you consider if you want to control the velocity of a satellite, if you want to control the velocity of a satellite, the aerospace engineer needs to estimate the altitude of the satellite. And in order to control the position of the shafts of the electrical, shafts, the electrical engineer needs to estimate the currents through the windings, right? So this is why actually the state estimation is important. And sometimes what happens is the states are interesting in their own right. Like sometimes the engineer wants to know the condition of the system. Suppose if we need to estimate the internal behavior of a system using state estimation algorithms, an aerospace engineer needs to estimate the position of the satellite in order to properly schedule its future activities. Okay, so therefore, the state estimation plays very important role to find the future behavior of any system or process. The mathematical modeling of this view of state estimation is shown here. You can see the mathematical view of the state estimation. So for a specific application, so see here, it comprises with the three modules: the dynamic system and measurement system and the state estimator. So here the dynamic system gives you the states of the system based on the system error source. So the dynamic system means like an electrical system or mechanical system or communication system or biomedical system, anything, any system. So it has basically some internal variables, right, which are called states. So just now we have discussed for a satellite, its a velocity, position. So these things are the states. So the dynamic system estimates the states like its position, velocity, or temperature, voltage, concentration, all these things. But the thing is, these states are not directly measurable. Okay, so they must be estimated using available measurements. They must be estimated using available measurements. So here, taking the measurement errors into account, the measurement system provides the measurements. And here the state estimator takes the measurements into account and take the previous information and gives you the future state of that particular system. So this is actually the thing happened in the state estimators. This is happened in the state estimator. So the dynamic system generate the system states based on the taking the system errors into account and measuring system. So suppose if you consider the satellite system, so the input states of the satellite system, suppose if you consider that it is its position, velocity, or acceleration. Okay, so these are the states of the system, and these states are continuously monitored by a measurement system like a radar. So radar will always monitor the states of this satellite system. Okay, so considering the measurement errors also into account and gives the measurements here. Okay, so that means what is taking the measurement errors into account, it gives some measurements here. So taking these measurements and previous information, the state estimator is going to give you the future state of the system. So that means suppose xk is the a priori state, and taking the measurements, the previous measurements into account, present measurements into account, xk plus 1, which is the future state of that particular system, dynamic system. So what is the next position of the satellite is going to be given by this state estimator taking the previous information as well as the measured information, like estimating velocity from noise position data, or estimating heart rate, suppose in the biomedical applications. So it is going to estimate the heart rate variations from ECG, or estimating channel coefficients in wireless communication, or estimating glucose level in biomedical devices. So this is actually the important mathematical view of this state estimation. Okay, so to do this systematically, the entire mathematical representation. So the it basically requires a tool, mathematical tool. So here we have the different state estimators. Here I have mentioned some of the state estimators, like Kalman filter is one such state estimator, extended Kalman filter, unscented Kalman filter, particle filter, interacting multiple model filters. So based on the application, based on the constraints, specifications, so we may choose one among the different types of state estimators even. So here, as I have mentioned, this state estimation needs a mathematical tool. It requires a mathematical tool. So a dynamic system has uh, what we call the state estimation, which is a mathematical framework, is required to describe how dynamic system evolves over the time. So state space model is such a model. So dynamic system has internal variables, right? Which are called states, like its a position, velocity, temperature, voltage, and so on. So these states are often not directly measurable, as we mentioned. So we must be estimated using available measurements. We must estimate them using the available measurements. So which can be done by using a special tool, mathematical tool, which is known as the state space model. So estimation, Kalman filtering can be done through a specific theory, which is known as state estimation theory. And the state estimation requires a mathematical tool which is a state space model. State space model is a tool in order to measure the state estimations. In order to measure the state estimations. So, in order to perform the state estimation, as we require a mathematical tool. So, any system that concerns with the mathematical modeling is likely a candidate for the state estimation. So, the tools of mathematics can be used for modeling and thereby control the states of the process and can find the information about that particular process. So, state space model is one such best mathematical tool in which the states of the system are represented by a numerical vector and is very important for current researchers even. So, we can use this state space model as a mathematical tool for many applications even. So, we have the different state space models. So we have two different state space models, linear models as well as the non-linear state space models. So based on what type of system it is, whether the system is linear system or non-linear system, we can adopt the linear model approach of mathematical model of state space model or non-linear state space model. So many researchers have concentrated on linear approach as it is simple, but most of the real world problems like tracking or navigation applications, so they are completely non-linear in nature. So because the dynamics of the system are completely non-linear. So some problems have linearization, which is uncontrollable near interesting working fields. So linearization is not effective in such cases. And some problems are simple and valid, but its validity is confined to finite domain only. And some problems are completely external. So where the linearization is ineffective in that particular case. So uh, we are going to concentrate especially on the non-linear models only. Non-linear models. So system models, these state space model concern with two submodels even. The state space model is subdivided into two model. One is the process model and measurement model. So the complete mathematical approach of state space model comprises with the two submodels, process model, which is also known as the propagation model, and second one is measurement model or observer model or otherwise. So this propagation model or process model, so it describes how the state propagates in time based on the external influences like input or noise, how the state propagates. It gives how the states propagate. Whereas a measurement model, so this model describes how measurements are taken from the process, so typically simulating noisy measurements. So these two submodels are defined both for the linear as well as the non-linear process. But the way of representing mathematical formulation is different for linear and non-linear process. But for any linear system or non-linear system, these two models are very important. So if you see, this is the linear state space model. So as our ultimate goal is to estimate the future behavior of the system, right? So xk plus 1 is equal to ak xk plus bk uk plus wk. This is the propagation model. If you observe, this is linearly, it is a linear fashion. It is arranged in the linear fashion and measurement model. So this is also linearly elevated, right? So here these functions can be expressed by using these matrices A, B, C, W, and V. So these W and V indicates the propagation noise and V indicates the measurement noise. So if you see the nonlinear state space model, so here the future state is expressed as a function of the three variables. So xk is the present state. UK indicates the input state. WK indicates noise. So similarly here also, xk is the input state, and vk indicates the measurement noise. So if you observe here, the future state is expressed as function of these three, whereas in the previous case it is a sum. So it is a summation, so linearly approximated. So the next state is given as a linear combination of state, input and noise, whereas here it is non-linear function, it is a function. So Kalman filter basically adopts this state space model in order to find the future behavior of the system. So Kalman filter is a well-known adaptive filter algorithm, widely used for the tracking applications especially. So here in the Kalman filter, so we use the linear the combination of state, input and noise, and also the observation model is also represented as a linear combination only, linear combination only. So here, this is actually the Kalman filter steps. How actually we are going to deal with Kalman filter. So initialization, and it involves the predicting the prediction and updation, taking the new measurements into account, and again the process continues. So this is the Kalman filter, and the prediction can be done through these mathematical expressions. So the posterior information from the a priori information, how they are going to be predicted, and how the correction is going to be considered by taking the Kalman gain kk. So these are the things. So here I'm going to explain it with respect to one example. So suppose if you consider a vehicle which is going in a straight line, vehicle which is going in a straight path. So this is the vehicle. Okay. So we want to mathematically model how a vehicle moves along the straight path. So in this particular case, first you have to observe what is the input and what are the state variables, means states, and what is the output. So participants, can you give any inputs? What would be the input we have to give in order to move this particular vehicle, students, participants?
Force.
So acceleration, we need to give acceleration, right? So acceleration becomes the input. So this acceleration basically controls the velocity. So input is velocity, which is controlled by the acceleration. Obviously, output is the measured position. So here the state variables are position and velocity are the state variables. Position and velocity are the state variables. So this is actually the standard example in Kalman filter theory, which represents a linear dynamic system. So for a linear dynamic system, I think everybody is aware of. So we'll use kinematic equations. So we have three equations. The V is equal to U plus AT, and S is equal to UT plus half AT square, and V square minus U square is equal to 2AS. So we are familiar with all these three equations, right? So we are using these two equations since our state variables are position and velocity. So here the position S is represented as ut plus half at square, and velocity is represented as u plus at. So xk is the state variable, the state of the system, and the variables sk and vk, which are position and velocity, are represented like a state vector sk and vk. And our ultimate goal is to find the future state of the system, future state of the dynamic system or a vehicle or whatever it is. So the position, the future position is the previous position plus this ut plus half at square. And also here we have introduced the noise component, that is the process noise. This is the process noise. And similarly, the velocity is, so the velocity is previous velocity, initial velocity plus at plus WK, so which indicates the process noise. So these two equations are propagation model in our state space model. And now in order to update the states, we need the observation information or measurement information, where the measurement information is given by Y. So measurement information is given by Y. So here if you observe, so this is xk, right? So you can represent xk plus 1 by using these two equations. By using these two equations, xk plus 1 can be defined using a linear state space model. Linear state space model. So xk plus 1 is sk. So the matrix and sk and vk, right? Sk and vk. So sk is, the coefficient of sk is 1 and coefficient of vk is t. Okay, so therefore here it is 1 and t. And vk plus 1, for vk plus 1, since there is no coefficient for sk, since it is independent of this position, so the coefficient for sk is 0 and coefficient for ak is, the coefficient for vk is 1. Coefficient for vk is 1. So xk plus 1 is defined as 1 t 0 1 and xk. This is the previous state sk and vk plus the input state. So the input, what input we are going to give is acceleration. So for sk plus 1, the acceleration is ak t square by 2. So the coefficient of ak is t square by 2 and the coefficient ak is here is t. So t square by 2 and t square by 2 t ak. So this is input state. This is previous state and this is input state and this is noise. Wk is the noise. And now yk is the output state. So output is obviously 1 0, since output is the position sk and vk. So the output is position only. So therefore 1 0 xk plus this zk indicates noise in measurement system, measurement noise. Wk indicates process noise, zk indicates measurement noise. So here the complete these noises are represented by the autocovariance of the process noise, which is given by expectation of wk transpose, and autocovariance of the measurement noise, autocovariance of measurement noise zk transpose. So the covariance between the positional noise and velocity, so we have to calculate. So even for the within the position we have the noise and velocity we have the noise, and also covariance between position noise and velocity has also to be considered, since covariance is a statistical measure, right? So that tells you if they increase together, positive covariance. If one increases while the other decreases, negative covariance. If they are independent, zero covariance. So these covariances indicates the noise interference in the system, noise interference in the system. So in this, so this is how we can first model the system, dynamic system. So we have considered the system as a vehicle which is going in a straight line. So for that system, using these kinematic equations, we have modeled the system using state space equations. And then we have to find out the what we call the estimation we can do it. So in this example, so let us consider the acceleration is 1 feet per second square, and standard deviation of acceleration is 0.2 feet per second square, and position is measured with an error of 10 feet at 10 times per second. So that means we are taking the measurements uh, 10 times in a second, 10 times in a second. So the complete the efficiency or the performance of the system depends on how good the measurements are, how good the measurements are. So you can take 10 measurements per second, or 100 measurements per second, or 5 measurements per second, like that. So based on the accuracy that we require, and based on the system specifications and all, so we can have the measurements, we can take the measurements. So since we are using simulation only, so you can take the you can use different measurements. Okay, so that you can compare the analysis, you can compare the performance analysis of the system for different measurements even. So but other things also, so if you increase the number of measurements, obviously the computational complexity increases anyways. So here A is equal to 1 feet per second square acceleration is given, and noise in acceleration, that is the standard deviation, is 0.2 feet per second square was given, and here time taken for each measurement is obviously 1 by 10, so 0.1 second. So one the measurement is taken for every 0.1 second. And here you can replace t is 0.1. So from the previous thing, 1t 0 1, so you can replace t with 0.1, and t square by 2t. So here we have replaced all these things. So we have given the real-time values for this state space model. So we know that S is equal to ut plus half at square, right? So S is proportional to the acceleration. So S is proportional to acceleration. And V is proportional to, here also, V is proportional to acceleration. So you can observe these things. So Y means, so since we need to provide the system noise, propagation noise. So the noise due to uh, uh, propagation noise, the propagation noise, that is the variance of position noise is proportional to half a t square, that the sigma a into t square by 2 whole square. Since s proportional to at square by 2, s square proportional to at square by 2 whole square. So sigma s square proportional to sigma a t square by 2 whole square. So here sigma a is a standard deviation, that is the noise content, so which is given by 0.2 feet per second square. So therefore it is 0.2 into, so that sigma s square is 10 power minus 6. In the similar fashion, the variance of the velocity is sigma v square. So that means positional noise, here we have calculated the positional noise and velocity noise, only positional noise and velocity noise. But the thing here is the covariance between positional noise and velocity has to be calculated, so which indicates how errors, so errors means uncertainties in position are related to errors in velocity. Okay, so that's why here the covariance of position noise and velocity is given by this equation. So during the position, how this velocity interferes. So that can be done by the covariance of position noise and velocity. So which is given by the product of standard deviation of positional noise, position and velocity. So already we have calculated the standard deviation variance for these two things under roots here we have considered, so that the covariance we have calculated here. So the covariance matrix is given by expectation of WK transpose. So WK transpose means WK indicates what is this? Noise is standard deviation in position, standard deviation in VW. standard deviation in velocity, and here it is it's a transpose. Okay, so that we'll be getting SW square, SW VW, VW SW, and VW square. So which indicates the covariance matrix. So this covariance matrix is, it indicates the noise, the propagation noise, So here this WK is replaced with this propagation noise matrix Q. So now we will use all the Kalman filter equations, so prediction and updation, so which can be done by all these equations. Okay, so these are the equations. So once I have given all these equations and calculate after giving these equations and running the MATLAB code. So these are the results I've got. So this one indicates the true state, and the green line indicates the measurements, where the measurements are taken. 10 measurements are taken per 1 second. That is 0.1 second one measurement, and this black line indicates the Kalman filter. So if you observe the true state and the Kalman filter, after estimating it, the Kalman filter achieves in estimating the true state. Okay, so this is how actually we'll use a state estimation. So that means the future estimations can be made by using the Kalman filter, using these state space models. So this Kalman filter is optimal estimate for linear system models. So this filter is a optimal filter, but it is applicable only for the linear systems, linear models. So where the input and states, everything is linear in nature. And one more thing here we have considered is noise also. Noise is also linear noise and additive noise. Additive noise means we can consider the Gaussian noise only. So for non-linear states, non-Gaussian noise, the Kalman filter won't work. So only linear for linear applications only will use the Kalman filter. So for non-linear applications, we can use some other Kalman based filters are being used, which are known as extended Kalman filter, uncentered Kalman filter, particle filter, and interactive multiple model filters. So different filters are there, but the thing here is the basic concept involved in this all these filters are like state space modeling only. So this is one of the fine mathematical approach. So so I'll show one video, students, to you. Is it visible, student participants? Is it visible?
No, madam. Only slide is visible. Video content is not visible, ma'am.
Not visible. Okay. Okay. 1 minute. Is it visible now?
Yes, ma'am.
Okay.
In this video, we'll discuss why humans use Kalman filters. If you're not familiar with the topic, you may be asking yourself, what is a Kalman filter? Is it a new brand of coffee filter that removes the taste in coffee? No, it's not. The Kalman filter is an optimal estimation algorithm. Today we'll discuss two examples that demonstrate common uses of Kalman filters. In the first example, we'll see how Kalman filter can be used to estimate a system state when it cannot be measured directly. To illustrate this, let's go to Mars before anyone else does. If your spacecraft's engine can burn fuel at a high enough temperature, it can create thrust that will let you fly to Mars. By the way, according to NASA, liquid hydrogen is a light and powerful rocket propellant that burns with extreme intensity at 5,500 degrees Fahrenheit. But be careful because a too high temperature can or anyone else does. If your spacecraft's engine can burn fuel at a high enough temperature, it can create thrust that will let you fly to Mars. By the way, according to NASA, liquid hydrogen is a light and powerful rocket propellant that burns with extreme intensity at 5,500 degrees Fahrenheit. But be careful because a too high temperature can put the mechanical components of the engine at risk. And this can lead to the failure of some of the mechanical parts. If that happens, you might be stuck in your small spacecraft, where you got to eat from tubes. To prevent such a situation, you should closely monitor the internal temperature of the combustion chamber. This is not an easy task, since a sensor placed inside the chamber will melt. Instead, it needs to be placed on a cooler surface, close to the chamber. The problem you're facing here is that you want to measure internal temperature of the chamber, but you can't. Instead, you have to measure external temperature. In this situation, you can use a Kalman filter to find the best estimate of the internal temperature from an indirect measurement. This way, you're extracting information about what you can't measure from what you can. Now that you know the solution to your problem, you can continue your journey to Mars. But are you scared of traveling in space? Let me tell you this. On Mars, you're gonna weigh 62% less than what you weigh on Earth. Still not convinced? Okay, then let's go back and take a look at another scenario that takes place on Earth. In this example, we're going to see how a Kalman filter can be used to estimate the state of the system by combining measurements from different sources that may be subject to noise. You have guests visiting from overseas, and you need to pick them up from the airport. You're using your car's navigation system. Let's look at the sensors you have on board, which help you find your position and navigate you to the airport. The inertial measurement unit uses accelerometers and gyroscopes to measure the car's acceleration and angular velocity. The odometer measures the relative distance traveled by the car. The GPS receiver receives signals from satellites to locate the car on Earth's surface. If you live in Boston as I do, you've got to travel through the Big Bend, a very, very long tunnel. And in the tunnel, it gets harder to estimate your position through GPS, since the receiver's line of sight to satellites is blocked and GPS signal is weak. In this case, you may want to trust the IMU readings, which give you the acceleration. However, acceleration itself doesn't tell you much about the car's position. For that, you need to take the double integral of the acceleration. Unfortunately, this operation is prone to drift due to small errors accumulating over time. To get better position estimates, you can use IMU measurements along with odometer readings. But note that odometer measurements may be affected by the tire pressure and road conditions. To summarize, your sensors measuring the relative position of your car give you fast updates, but they are prone to drift. The GPS receiver provides your absolute location, but it gets updated less frequently and it may be noisy. In this scenario, a Kalman filter can be used to fuse these three measurements to find the optimal estimate of the exact position of the car. Let's look at some facts about Kalman filters. The Kalman filter is named after Rudolf Kalman, who is the primary developer of this theory. It is an optimal estimation algorithm that predicts a parameter of interest, such as location, speed, and direction in the presence of noisy measurements. Common applications of Kalman filters include guidance, navigation, and control systems, computer vision systems, and signal processing. One of the first applications of Kalman filters was in the 1960s. Do you have any guesses as to what it helped with? Engineers used it in the Apollo project, where the Kalman filter was used to estimate trajectories of the manned spacecraft to the moon and back. Let's summarize what we've seen in this video. Kalman filters are used to optimally estimate the variables of interest when they can't be measured directly, but an indirect measurement is available. They are also used to find the best estimate of states by combining measurements from various sensors in the presence of noise. In the next videos, we'll cover what Kalman filters are.
So, hope you understand this concept, participants. Is my screen visible?
Screen visible, ma'am, but the PPT is not visible.
PPT is not visible. Okay. Okay. Is it visible now?
Ma'am.
So, as mentioned, this Kalman filter is especially used for the linear applications, but most of the communication applications or biomedical applications, so they are the dynamics, the system dynamics are completely non-linear. So we will be using the different types of filters, Kalman based filters, extended versions of the Kalman filters, and multiple Kalman filters, multi-modeling filters are also been used. So where the same principle is normally been used here also. So participants, you can try this one, understand the aircraft dynamics. So you can try generating the state space modeling for this one. So here, if you observe for the aircraft dynamics, the states are used here U of t, W of t, like forward velocity perturbation and vertical velocity perturbation and pitch rate, pitch angle, altitude. So these are the input states, and so number of states even depends to participants. So here we may use a 3-state longitudinal model or 5-state longitudinal model and 7-state model also. So based on the number of states we are considering, so obviously the complexity, mathematical complexity increases, but we'll get the ultimate results. So these are the inputs, and the measurements are like a pitch angle and altitude. So these two are the measurement outputs we are taking, and based on these two things, so you can model the longitudinal dynamics. By using these longitudinal dynamics, you can estimate using the Kalman filter. So these are the equations. So please try once. So that you can apply it for any application in any field. So in any research fields, I hope most of you may pursuing your PhDs. So you can use this state space modeling approach in order to apply for your own application. So these adaptive filters are extremely important in real-time communication systems where channel characteristics change. So these filters adjust their coefficients automatically based on error feedback. So uh, we have adaptive filters like LMS filter and RLS filter. Like LMS is simple, low complexity and widely used filter, and RLS is fast convergence but more complex filter. So applications include like acoustic echo cancellation in VoIP or adaptive channel equalization and noise cancellation in headsets and interference suppression in receivers. So these are the some of the applications. So these adaptive filters basically uh, adaptive filters are the bridge between the classical filtering and the intelligent systems, especially when the environment is unpredictable. So adaptive filters adjust itself to minimize error changing in environments, and RLS or LMS algorithms are widely used in communication receivers. And Kalman filters, as we have seen, now it provides optimal estimates, estimation in dynamic systems. And all these different techniques are essential in communication systems, sensor networks, radar, robotics, and modern AI-driven systems even. So AI-driven signal processing is another important aspect. So traditional filters depends heavily on mathematical models, as we have seen just now. So as the number of states increases or the state dynamic complex dynamic systems, the mathematical modeling is obviously a complex mathematical model we need to develop. But AI-based models learn directly from the data. So we need not bother about taking these equations, writing these equations and all. So that learn directly from the data, and accordingly we are going to give the better results. So we have different techniques here in the AI-based approaches in signal processing. So in this one, neural networks. So neural networks is one such thing. So which actually learn patterns in data by adjusting internal weights to approximate complex nonlinear relationships in signals. And CNN is convolutional neural networks. So this is for spatial and spectral filtering. So where it is used for extracting the spatial features like images, grids, so and spectral features like frequency components and so on. So they perform filtering through learnable convolutional kernels. And RNN is another one. RNN is a recurrent neural network, and LSTM is a long short-term memory. So these are for the time varying signals. These models basically capture the temporal dependencies, making them ideal for signals that change over time, like speech, sensor data, or communication signals. And deep encoders, deep auto encoders. So this is for the denoising. So these autoencoders is a neural network which is used to learn compressed representations. So deep autoencoders learn to reconstruct clean signals. So by removing the noise in the encoding and decoding process and so on. And GAN is another one. So this is generative adversarial network. So this is for generating the clean signals once again. So this uses a generator plus a discriminator to create synthetic clean signals. So that match the distribution of real clean data. So these are basically useful for denoising, signal reconstruction, data augmentation, and all. So why actually these AI models are superior to traditional filters means AI-driven models overcome the key limitations that were existing in the classical filters like Wiener filters or Kalman filters or LMS, RLS, and so on, because they can handle non-linearities. So this is one of the major thing. So they can handle non-linearity. So traditional filters assume linear models or approximate the non-linear systems as if they are linear. But AI models learn non-linear mappings from the data itself. And also they adapt to non-stationary noise also. So if you see in the Kalman filter, so we have considered that it is a additive noise and Gaussian noise. But these AI based models adopts the non-stationary noise. So real world signals have noise that changes over time. So deep models dynamically adapt to varying parameters. And another important thing is learn directly from the raw data. So no need for handcrafted models or assumptions and so on. So directly they learn from the raw data itself, and they provide end-to-end learning. So filtering plus feature extraction happen in one integrated architecture. Okay, so neural networks can learn complex patterns even in the presence of noise. CNN learns spatial and spectral features, and RNN and LSTM learn time varying signal behavior. Okay, and auto encoders learn to denoise the signal, and GAN can generate the clean versions of the noisy signals. So this data driven approach allows AI to overcome the limitations of classical filters, especially in non-linear, non-stationary communication environments. And AI for filtering and denoising. So AI-based filtering techniques are revolutionizing and signal processing. So deep denoising autoencoders can handle complex noise patterns that classical models cannot describe. So similarly, CNN-based filters. So they are widely used in image denoising, speech enhancement, and so on, even in the radar signal cleanup, RF fingerprinting, and so on. And GAN-based denoising produces highly realistic clean signals and is useful in satellite communications and also in medical imaging. And AI-driven adaptive filters can update in real time without needing explicit mathematical models. So that is the ultimate thing in the AI-based adaptive filters. So no, without needing any explicit mathematical models, so we can use these models for getting the better results. So if you observe these AI in communication applications, so we have noise reduction in wireless communication systems, channel estimation, modulation recognition, spectrum sensing, beamforming, and so on. Madam, so can I continue for 10 more minutes?
Okay, madam. Okay.
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 So, so if you see one practical application, we'll analyze AI in is it visible? AI enhanced noise reduction in wireless communication system. So here, in modern cellular and wireless networks, 4G, 5G, 6G received signals are often heavily corrupted by the interference and fading and ambient noise. Where AI-driven noise reduction uses uh, these machine learning or deep learning algorithms, models to clean the signal before demodulation and improving clarity as well as the reliability. So here the problem addressed is the traditional signal processing methods like Wiener filters or spectral subtractions are limited in highly non-linear or dynamic environments, right? So wireless channels in urban areas change rapidly due to mobility or multipath and interference from the devices. So here AI-driven techniques like deep neural networks or recurrent neural networks like LSTM are trained on large data sets of noise and clean signals. So the model learns complex noise patterns and predicts the clean signal from its noisy version. So even in 5G, 6G research, denoising auto encoders and transformers are increasingly used. So here, how basically it works means it collects noisy wireless signal samples first. It collects noisy wireless samples for signal samples first and pre-process that information by using FFTs or normalization or framing. So different techniques are available, and then training. So train AI model with paired noise versus clean signals. So it trains the model with paired with noise as well as the clean signals, and then deploy a model in the receiver for real-time denoising, and finally send the cleared signal to demodulation or decoding blocks. So these are the different works that has been done in the AI driven signal processing. First, collecting the noisy wireless signal samples and pre-processing the data, and train AI model with paired noise as well as the clean signals, and then deploy model in the receiver, and finally send the cleared data. So if you proceed with all these things, the key performance improvements are signal to noise ratio. So it leads towards a higher signal to noise ratio after denoising, and reduced bit error rate, especially in low SNR conditions. So especially in low SNR conditions, bit error rates are very high. But in AI-driven systems, the reduced bit error rates, especially under low signal to noise noise ratio conditions exist, and also the quality of service, especially in voice, video calls, IoT links, and also adaptive to varying noisy environments. Okay, so these are the different things we can achieve. So here, under these circumstances, if you the performance measured at low to moderate signal to noise conditions, noise ratio conditions, from -5 dB to 10 dB in fading interference wireless channel. I have done it under these conditions for different filters, different signal processing techniques. So Wiener filter, Kalman filter, and also AI-based approach, deep learning denoiser, CNN LSTM approach, and see under -5 dB, where the signal to noise ratio is under very low conditions. So I'm getting good results under such circumstances. Bit error rate is 0.12 at -5 dB. So lower conditions. So AI-based denoising obviously improves the bit error rate by 40 to 70% over traditional filters. So especially the maximum benefit occurs at the low signal to noise ratio. So where classical filters fails under such conditions. And also the signal to noise ratio improvement. So if you see the deep learning based denoiser have the output signal to noise ratio higher when compared to the other two techniques. And error vector magnitude also in denoiser, AI denoiser, it is 4.9%. So here the quality service metrics like throughput, latency, packet loss, robustness to interference, adaptability to channel variation. So there in AI-based denoising, they shows better results when compared to the traditional filters. Traditional filters. So at least 10 to 25% higher with respect to throughput, and latency is low to moderate because it depends on the model size, right? And packet loss is 30 to 50%, and robustness is high, adaptability is strong. So these are the advantages with the AI-based denoising. So the first and foremost thing is it doesn't require any explicit mathematical modeling, and it learns from the raw data itself. So in real world use case, telecom companies use AI denoising in 5G based stations to improve uplink performance. Even in IoT, edge devices use lightweight models to filter sensor noise. Even in the satellite communication uses AI in order to suppress the atmospheric interferences. But still it has got some limitations since it requires a large data sets for training, and computational cost must be optimized for real-time implementation. And also the model performance may degrade if channel characteristics change drastically unless retrained. So it has got some limitations also. So these are the results I have given. And these are the comparative analysis. Comparative analysis, here it is, for different techniques. And this is another example, even for the biomedical application, A-based ECG arrhythmia detection application. So this is here also electrocardiogram signals are used to diagnose heart rhythm disorders such as arterial fibrillation and so on, and ventricular arrhythmias and so on. So AI-driven model automatically analyze ECE waveforms and classify abnormal patterns more accurately than traditional rule-based methods. So here also basically the signal processing steps in AI-driven signal processing for this particular application includes pre-processing, feature extraction, classification. Okay. So here the traditional ECG analysis depends heavily on manual inspection, fixed thresholds, and simple morphology-based algorithms. Whereas AI model learns a complex variation in ECG and subtle abnormalities and patient-specific patterns. Okay, so based on this one, accuracy, sensitivity, and early detection improves significantly. So AI-driven signal processing enables accurate automated detection of cardiac arrhythmia using ECG signals by combining noise removal, deep feature learning, and intelligent classification. And AI improves obviously the diagnostic accuracy, and it supports wearable health monitoring and enhances outcomes in modern biomedical engineering. And if you see, these are the future directions. So the future of filtering lies in combining classical methods with the AI. So classical methods is not actually obsolete. So we'll get the better results when we fuse it with the AI, fuse it with the classical models. Hybrid AI model-based filters can leverage both the theoretical guarantees and learning capabilities. We'll see the self-learning optimum filters which are designed for the 6G networks. Edge and IoT devices to run intelligent signal processing locally. And quantum techniques may enhance filtering performance at very low SNRs. So these technologies together will define the next generation communication systems. So the optimum filters like Wiener or Kalman filters or LMS, RLS. So this forms the backbone of communication receivers, and adaptive filters allow systems to adjust automatically in dynamic environments. Whereas AI-driven filtering opens the door to intelligent, flexible, and high performance signal processing, which is critical for 5G, 6G, and IoT systems. And the future communication systems will rely on the synergy of classical optimum filtering and artificial intelligence to achieve robust and efficient signal estimation. So these are the some of the references, and thank you for your kind support and patience. So if you have any doubts,
Participants, if you have any queries, please raise. The forum is open for you. You can post your queries in the chat box also.
Okay, madam. Thank you.
Thank you so much,
Thank you,
madam. In your hectic schedule, you have invested your valuable time for this FDP. Now, I would like to give the summary of your valuable insights, madam. Dr. B. Leela Kumari, ma'am, have delivered an incredibly insightful and knowledge-rich session today. She detailedly explained on optimum filtering, state estimation theory, and AI-driven signal processing. She has given a deep understanding of the mathematical foundation, practical significance, and real-world applications of modern signal processing techniques. Ma'am has clearly explained about Wiener and Kalman filters, linear and nonlinear state space models, noise modeling, and dynamic system estimation. I hope the participants gained valuable insight into how these techniques form the backbone of advanced communication and radar systems. Ma'am also highlighted the immense potential of AI enhancing filtering, ranging from deep denoising methods to neural network based channel estimation, which is shaping the future of 5G, 6G, IoT, and intelligent communication networks. Ma'am also discussed about the challenges such as noise interference and time varying environments, and how optimum filters help overcome these limitations has enhanced our practical understanding of real-time engineering scenarios. The examples from radar, sonar, tracking systems, navigation, and communication channels were especially enlightening and helped connect theoretical concepts to applied research. Thank you so much, ma'am, for your valuable insights for this FTP.
Thank you, madam. Thank you for the opportunity. I thank Venkateshwara garu, TV Rao garu, and also Vishnu Priya garu and Hamlata garu for inviting me for this prestigious Atal FDP. And thank you, my dear participants, for your patience listening. Thank you, one and all.
Thank you, madam.
Dear participants, next we have back-to-back sessions by Dr. Ashraf Ali Sheikh. Sir, yesterday already he took one session and he explained hands-on training related to quantum. Now he will continue the same hands-on training, quantum as well as VLSI. I'll give the brief intro of Dr. Ashraf Ali, sir. Sir, Ashraf, sir.
Yes, ma'am.
Okay, sir. Sir, let me introduce you to the participant, sir. Dr. Ashraf Ali Sheikh is an accomplished professional with expertise in teaching, guidance, and counseling. He has a strong track record of in improving research activities and teaching effectively, with a PhD in ECE from KL University. Sir has published several papers in national and international journals like Web of Science, Scopus, and UGC CARE journals. With over 16 years of teaching experience, Sir has received many awards. He is the recipient of Best Teacher Award by NRI Institute of Technology for the academic year 2021 to 22. His field of expertise involves VLSI design, machine learning, and deep learning. Sir is currently the director of BIS Technologies Private Limited. Thank you so much, sir, for accepting our invitation, and please continue the session, sir.
Sure, ma'am. Thank you. Thank you very much. Today we yesterday we discussed, ma'am. Is it visible?
Yes, sir, it is visible, sir.
Yeah, thank you, ma'am. Yesterday we discussed about the difference between classical and quantum computing. Quantum computing with cloud and backend. So quantum gates as reversible gates, and quantum gates as unitary operators, and with the gates with the single qubit, 2 qubits, and 3 qubits. And we solve some circuits, that is series quantum circuits and parallel quantum circuits. So, and also we discussed about entanglement state with an experiment, right? So today we will solve some more problems, and then we will go to quantum error corrections. This is most important topic, quantum error correction, right? So here there are 5 types of quantum error corrections. So first one is bit flip error, bit flip error. Second one, phase flip error, phase flip error. Third one, Shor code technique. And then fifth one, Steen error technique. And then one more thing is there, that is surface code error technique. So these are the 5 most important error correction techniques. In this, out of 5, most widely used are bit flip error, first one, phase flip error, and then Steen code error. So we will discuss today about these 3 error detection techniques, error detection and correction techniques. So first one is bit flip error, second one phase flip error, third one Steen code error. And then after that we will solve some more problems, and then we will move on to Quiskit, right? So yeah, I have completed all these things yesterday with Algar set also. So we know how to calculate the outer product, how to find the equations of X, Polis X gate, Polis Y gate, Polis Z gate, Hermat gate, and phase gates like S and T gates and all. So Toffoli gate and Fredkin gates. Yesterday we discussed everything. So we discussed about series quantum circuits and parallel quantum circuits also. So second, yeah. So entanglement state. So entanglement state already we discussed yesterday, but still it is most important topic. So we will refer one more time. Okay. So entanglement definition. What is the definition of entanglement state? Suppose if 2 or more particles are connected, if 2 or more particles are connected in such a way that if the state of the one particle decides the state of the other particles or determines the state of the other particles, right? So that is the definition of entanglement. So let us consider an experiment. So we already discussed yesterday, no need to discuss again. So see how to construct the entanglement state or Bell states. Today we will see. Okay, so these are the theory part. Yeah. So first of all, you need to apply ket 0, ket 0. The circuit diagram is the same. The quantum circuit diagram is same for all the Bell states. Actually, Bell states or entanglement states are of 4 types. 4 types, right? We represent it as beta 0, 0, beta 0, 1, beta 1, 0, beta 1, 1. So see here. So first of all, the circuit is the same, but the inputs are different. Here we are applying ket 0, ket 0. Next, ket 0, ket 1. And then ket 1, ket 0. Finally, ket 1, ket 1. So the circuit is the same. So see here, first of all, we have to calculate manually. Then after, we move on to the tool. Okay. So first of all, we will start the circuit from In the quantum circuit, we'll start the circuit simplification by starting from right side. So first of all, you are having a controlled X gate. Suppose if the line is not present, then we simply call it as NOT gate. Suppose if the control line, this line is present, then we call it as C0, control NOT gate. So control NOT gate and then Hadamard gate. Right? So since we are starting from right side to left side, so C0, put C0, control NOT, and then Hadamard gate, which is in parallel with a straight line. So whenever you find a straight line, you have to assume a identity matrix is present at there. So at that position, identity matrix is present. So therefore, Hadamard gate and identity matrix are in parallel. So whenever these two are in parallel, whenever you find two lines are parallel, then you have to put a tensor value or tensor product between those two. Okay, between those two lines. So in that line, you are having Hadamard gate. In that line, you are having identity matrix. So in that Hadamard and identity matrix, you have to put tensor product. And then ket0 and ket0 are also in parallel. So you have to put ket0. Since these two are in parallel, you have to put again tensor product. Okay, so we know ket0 tensor ket0 means 0, 0 or ket0, 0. So first of all, you need to calculate H tensor I. H tensor I. So H means 1 by root 2, 1, 1, 1 minus 1. Today we will see how you are getting this value by using Qiskit. Okay, so 1 by root 2, 1, 1, 1 minus 1. And tensor product of identity matrix 1, 0, 0, 1. So you know how to calculate, so tensor product value. So yesterday we discussed multiply this with the entire matrix. So here see 1, 0, 0, 1. Then after multiply with the entire matrix, again 1, 0, 0, 1. Next, multiply 1 with this entire matrix, again 1, 0, 0, 1. Multiply minus 1 with this entire matrix, then you can get minus 1, 0, 0, minus 1. Yes, correct. So that is the way to calculate the tensor product. Then after, you are finding C0. C0 means what? C0 means that is also a 4 by 4 matrix, correct? So 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0. This is the matrix equation. This is the matrix for C0. This is the matrix for C0, right? So C0, how you are getting? This is identity matrix 1. This is 0 matrix 0. This is identity matrix again 1. This is X. This is X. This is the expression for X, that is equal to 0, 1, 1, 0. Okay. So C0 means control X. CX gate is also called as C0 gate now. So that is the reason why 0, 1, 1, 0. Okay. Whenever you are finding C0 on the left side, on the left hand side, so what you have to do? Third, you have to interchange third and fourth rows. See here, third and fourth rows. You need not to take entire this thing and multiply with this thing. 4 by 4 matrix and again 4 by 4 matrix. You need not to multiply matrix multiplication. So you need to what? The technique, third and fourth rows are to be interchanged. So here see. So first, second, third, fourth. So see here, first, second, third, fourth. So 1, 0, minus 1, 0 becomes here 0, 1, 0, minus 1 turns here. So see here. Yeah, clear. So now multiply with this 1, 0, 0. How you got 1, 0, 0 from ket 0, 0? So ket 0, 0 can be taken as 1, 0, 0, 0. Ket 0, 1 can be taken as 0, 1, 0, 0. Yesterday we discussed. Ket 1, 0 can be taken as 0, 0, 1, 0. And then ket 1, 1 can be taken as 0, 0, 0, 1. 1, right? So since here get 0 0 is given, so that is the reason why we have taken 1 0 0 1 0 0. Okay, multiply this thing, then you can get this value. So 1 0 0 1. So that means what? This is get 0 0, this is get 0 1, this is get 1 0, this is get 1 1. So you have to take whenever a value 1 is found. So then the corresponding get operation, get value, that is get 0 0, and again here also then get 1 1, get 1 1. So this is called Bell state or entanglement state, because we are not in a situation to take a common value. So first value is here 0, but here is 1. Second value is 0. Here also second value is 1. We cannot take, or we cannot split. We cannot split. So whenever we cannot split the states, then we can say that the states are following entanglement state. Those two states are said to be linked together. Yeah. Next, see here, diagram is same, but values are different. Cat 0, now cat 1 is taken. Same thing. You have to apply from right side to left side. Then C naught, H tensor I, and then 0 tensor 1. So 0 tensor 1 can be written as 0 1. So 0 1 can be written as 0 1 double 0. And then take the tensor product between Hermite gate and identity matrix. Then you can get this one. Again, C naught is on the left side. So you have to replace third and fourth rows. Correct? So third and fourth rows here. So what is the third row? So third row becomes, so this row becomes here, and this row changes to here. Yeah, so that's it. And then multiply these two things. So you are getting 0 1 1 0. So that means get 0 1, get 1 0. Yeah. This is also, we call it as Bell state, because in the first state you are having 0, but in the second state you are having 1. So no need to, sorry, you are unable to take it as common. You cannot take 0 as common, or you cannot take 1 as common. In the second state also you are getting 1 and 0. So these two states are, sorry, this state is called as a Bell state or entanglement state. You cannot split the state. Similarly, 1 0. Then after 1 1. So see here also you are getting 0 0 1 1. And again here you are getting 0 1 1 0. So these states are called, these four states are called Bell states. Bell states. So let us consider the Algar set tool. Quick. Then consider Hadamard gate, and then control X gate. Control X gate. So this is only X gate. Control is nothing but a dot. So click it on and then place on it. So 0 0. You have taken 0 cat 0 cat 0. So then, one second. So net issue is there. So that is the reason why you are not getting the result. So net issue is there. 1 second. Can't simulate the circuit, does not support WebGL or has disabled. Okay. 1 second. Still showing the same problem. Okay, seems to be some net issue. Okay, you can try on it on your own. So first of all, put H and then control NOT gate. So control is taken from here. So after that 0 1. Then after 1 0 0. Then after 1 1. You will get all the bell states. Okay. So this is the tool, the best tool used for the simulation of quantum circuit. ALGA set. Here. ALGA set. ALGASSERT. ALGA set. Okay. So right. Next. Then after quantum error correction. Quantum error correction. So first of all, why the quantums are getting errors? Qubits are getting errors. We already discussed whenever the qubits are interacts with the environment. So environment contains dust, water, sound pollution, noise, etc. Whenever the qubits are interacted with the environment, then the qubit losses its superposition states. The qubit losses its superposition state. So we have to maintain the superposition state. Otherwise, we cannot solve the complex problems, which cannot be solved by the classical problems. So the difference between classical and quantum we discussed earlier. So what is the difference between the classical and quantum computers? The classical computers just used for gaming purpose or data storage purpose, like seeing the movies, etc. Correct. So whereas quantum computers solves the problems which cannot be solved by the classical computers. What are those problems? Factorizing a larger value, find database search, and then optimization. These are the major problems, major complex problems, which can be solved very easily by using quantum computers. Those problems, those applications cannot be solved by the classical computer. Correct. So first of all, you have to be clear that qubits are error free. So when the qubits get errors, that means whenever the qubit, what you call that one, combined with the environment, then the qubits losses its superposition state. Right. So see here, the goal of quantum error correction to detect and correct the errors. So here, first of all, let us consider a state. The state is called as alpha ket 0 plus beta ket 1 So this is the state, quantum state. And again, these two bits are called additional bits, ket 0, ket 0. So consider the diagram. So this is called control NOT gate, and this is also called as control NOT gate. So see here, in the quantum error detection and correction technique, we have to follow 3 steps. First step is to encode the data. Second step is syndrome calculation or parity check. It is also called as parity check. The third one is error correction technique. Syndrome is used to detect the error. After that, we have to correct the error by using the suitable gates, suitable quantum gates. First of all, encode the qubits. Second step is to detect the error. Third step is correct error by using quantum gates. You have to follow these 3 steps order. That is step by step. So see here, now in a first phase, you have to convert the qubits or encode the qubits. So see here, given ket 0 plus beta ket 1. So this is encoded into alpha ket 000 plus beta ket 111. How you are getting this one? So see here, first of all, let us assume 0, 0. So whenever control bit is 0, the target bit, whatever present here, this is the target bit, that will be transferred to the output. So that means 0. So here also 0, second one here also 0. So 0. Since here also 0, control bit is 0, so target bit is transmitted 0. So that means you are getting 3 zeros here. So that is why you are getting alpha ket 0, 0, 0. Now let us consider here 1. 1. Whenever 1 is present here, it will activate the C0 gate. So the target bit is flipped. So target bit is what? Ket 0. It is flipped to ket 1. And again, 0 is given since it is C0. And again, here 1 is there, control bit is 1. Again, C0 is activated. Control X gate is activated. That means it will flip the bit. And again, you are getting 1 here. Here also you are getting 1 here. Here also you are getting 1 here. So that is the reason why you are getting all ones. So this is called encoding process. So you are converting alpha ket 0 plus beta ket 1 to alpha ket 0, 0, 0 plus beta ket 1, 1, 1. This is the process called encoding. First step is done. First step is completed. Now, see here. Given alpha ket 0 plus beta ket 1, you are encoded it into alpha ket 0, 0, 0, 0 plus beta ket 1, 1, 1. After that, syndrome calculation or parity check. Parity check. So syndrome calculation is used for error detection. Error detection. After that, you need to be do error correction techniques. You have to perform error correction techniques by using suitable quantum gates. Yeah. So this is the encoded process. After that, syndrome detection. See here, the diagram is slightly modified. Syndrome detection. So here extra bits are added. So ket 0, again ket 0 is added. These bits are called ancilla bits. Ancilla bits. That means extra bits. Okay. So x1, x2, x3. So see here. Here dot is there. So C0 gate. Again dot is there. That means C0 gate. Again dot is there. This is also C0 gate. And then control bit is there. That means C0 gate. All are control NOT gates only. So here this line, from this line, you are getting S1 as x1 XOR x2. This is not a tensor product. A tensor product we can write like this, into mark. We know whenever plus is there and circle around it, it will represent XOR gate. So S1 is equal to x1 XOR x2 and S2 is equal to x2 XOR x3. x2 XOR x3. Correct. So let us check, verify. So 0, 0, 0 you have given. Whenever control bit is 0, so this is the control bit, this is the control bit, this is the control bit. So these are the target bits. Okay. So whenever control bit is 0, C0 is deactivated. So what happens when C0 is deactivated? It will transfer here directly, ket 0. Right. Next, here control bit is again 0. So this is also deactivated. That means this ket 0 value is transmitted to the output. That means whenever x1, x2 is 0, 0, then what happens? S1 is also equal to 0. Now, if you take 0, 1, 0, 1, 0, 1. So I am proving S1 is equal to x1 XOR x2. Okay. So 0, 1. See 0. So that is the reason why it will transmitted here ket 0. But here the control bit is 1. So whenever the control bit is 1, it is activated. Whenever it is activated, what happens? It will flip the bit. Ket 0 is there. then you will get ket1 here. That means S1 is equal to 1. Right? Next, then after 1 0. 1 0. See, control bit is 1. So this is activated. That means here the bit is flipped. The target bit is flipped here. And then since it is 0, it is deactivated. Second C0 gate is deactivated. The target bit 1 is transmitted. 1 is transmitted. Whenever 1 0 is there, 1 is transmitted. So final step 1 1. 1 1. Whenever 1 1 is found, so 0 flip to 1. Again 1. Since this is also activated, 1 is flipped to 0. So 1 1, then you can get 0. So hence, this is the equation. This is the table for XOR gate. So that is the reason why you are writing S1 is equal to X1 XOR X2. Similarly, you can find S2 also. For S2, you are getting X2 XOR X3. X2 XOR X3. Okay. So this is the circuit diagram for parity check or syndrome detection or error detection. Okay. So see how we can detect the error by using this table. So X1, X2, X3. Since 3 bits are present, we can write total 8 combinations, 2 power 3. So from 000 to 111. So for 000, so what is S1? So 000. For 00, again 0. 01, you will get 1. 01, you will get 1. 101. 101. 110. 110. So since S1 is the XOR of X1 and X2. Now S2, what is about S2? It is the XOR operation between X2 and X3. So since 0, 0, 0 is there. 0, 1, 1 is there. 1, 0, 1 is there. 1, 1, again 0. 0, 0, 0. 0, 1, 1. 1, 0, 1. 1, 1, 0. Right? You got the table? Understood the table? Right. So simple XOR operation. Right? So see here. 1 second. Yeah. Now you have to find the errors in the table. So how we get the errors in the table? See here. First of all, check 0 0. Here also 0 0 is there. So here you are getting 000. But here you are getting 111. That means both are same. No changes there. No changes is there. Here 0 0 0. Here 1 1 1 is there. So bear with me. You will understand slowly. So that means for 0 0, the error, no error. See here now for 0 1, you will understand here. For 0 1, you are getting it as 0 0 1. For 0 1, you are getting it as 1 1 0. Which bit is flipped? Which bit changed? See here, here 0, here 1, no change. Here 0, here 1, no change. See here. So, but here 1, but here 0. So change is there, right? So that means which bit? Third bit is flipped. This is third bit, na? So third bit is flipped. See, 1 0. For 1 0, you are getting 0 1 1. For 1 0, you are getting 1 0 0. Which bit is changed? First bit. First bit is changed. For remaining 2 bits are same. 0 0. Here also 1 1. So no change is there. But first bit is changed. So that is called first bit flip. Next 1 1. See here 1 1. For 1 1 0 1 0. Here 1 1 1 0 1. Which bit is changed? Second bit is changed. Second bit is changed. Hence, here I have written second bit is changed. Is there, it is clear, or anyone is having any doubt in this table? Please let me know. It is clear. Please respond. Here the table only the difficult thing. The remaining part is very much simple. Yeah. Shall I continue? Yeah, tell me. Shall I continue? Are you having any doubt? Clear? Okay.
Yes, sir. Please continue.
Okay, ma'am. Thank you. Thank you, ma'am. So, yeah. So, for 0, 0, there is no error. For 0, 1, you are getting third bit is flipped. For 1, 0, first bit is flipped. For 1, 1, you are getting second bit as flipped. So, you have to correct those things. So, in order to correct those things, what you have to do? You have to do error correction by using suitable quantum gates. That is what we have written here. See, yeah, we have to do the error correction by using the quantum gates, suitable quantum gates. Here, what is the suitable quantum gate? Means X gate, X gate. So you have to use the NOT gate. So whenever you find the error in that place, you have to put an X gate. So see here, for 0, 1, you are getting third bit error. So you have to put in the place of third bit an X gate. Similarly, for 1, 0, you are getting first bit is error. So you have to put in that place a X gate. So see here, the diagram is like this. So this is a little bit confusing. So how they have drawn? Yeah, I will show it here. Yeah. So see, so since you are getting for 0, 0, no error. Yeah. So second. Yeah. Expand these lines. Okay. So you are measuring here and you are measuring here. You are measuring here. Yeah. So this is 0, 0. This is 0, 1, 1, 0, 1, 1. So since S1, S2 are 2 bits, so we can get 4 possible outcomes: 0, 0, 0, 1, 1, 0, 1, 1. Okay. Whenever you will get a 0, you have to put anti-control there. Here also, you have to put anti-control there. So whenever you find 0, put anti-control. Whenever you find 1, you have to put control. Control means a dot, thick dot. Again, here also thick dot. Here also, here anti-control. Here thick dot. Here also thick dot. See here. So first of all, which gate is in error state? So for 0, 0, no error. For 0, 1, you are getting third bit as error. Third bit means this one. This one. So for 0, 1, you have to put an X gate here. You have to put an X gate here. Next, for 1, 0. For 1, 0, first bit is flipped. See here, first bit is flipped. So 1, 0, first bit is flipped. So you have to put an X gate here and then combine these two. Combine these two. Right. Last one, see. Second bit is flipped for 1, 1. So put X gate here and then combine these two controls. These two controls. Whenever you find, put control. Whenever you find 0, put anti-control. Right? So this is the error correction circuit. So since you are using the quantum gates, these are quantum gates. Right? So this is the circuit diagram for what? Parity check or error detection or syndrome detection, right? First, what we have to do? First, we have to convert the quantum state into encoded state. First step is done. Second step, you have to do parity check. That means error detection technique. Third one, you have to correct the error by using the suitable quantum gates. So see here, the diagram is the same. Now observe this thing. So since 0, 0, so anti-control, anti-control. 0, 1, anti-control. Since 1 is there, control. 1, control. See here wrong. Anti-control. Again, 1, control, 1, control. So for 0, 1, third bit is flip. That is the reason why I have taken X gate here. For 1, 0, you are getting first bit as error. So control X gate is taken here in the first bit position. Similarly, for 1, 1, second bit is flipped. That is the reason why you have taken X gate, control X gate in the second bit position. Yes. So this is the bit flip error detection technique. Bit flip error detection technique. Most important technique. Okay. So you can try this in Algar set, but I don't know why it is showing like this. Yeah, you can try by using Algar set. Same circuit diagram you can do it on your laptop. algarset.com. Okay, so same diagram. I will share the PPT. You can draw the diagram. Okay. Next, phase flip error. So phase flip error. So this is exactly opposite to that of bit flip error. Exactly opposite to that of bit flip error. So ket0 and ket1 are called Z bases. Z bases. Ket plus and ket minus are called as X bases. X bases in the quantum states. So X basis and Z basis. So phase flip error converts Z basis into X basis by using Hadamard gate. By using Hadamard gate. So first of all, ket0 is applied to Hadamard gate, and then ket1 is applied to Hadamard gate. So h of ket0 is equal to 1 by root 2 ket0 plus ket1. Yesterday we have done this one. H of ket0. H ket0 is equal to 1 by root 2. This is the formula. You have to by heart it. H of ket0 is equal to 1 by root 2 ket0 plus ket1. This can also be simply written as ket plus. That is what I have written here. Ket plus. So h of ket1 means 1 by root 2 ket0 minus ket1. Minus ket1. This can be written as simply ket minus. That is what written here. Ket minus. So whenever you find h of 0, h of ket0, you can simply write ket plus. Whenever you find h of ket1, you can write ket minus. Okay, right. Next thing. So see here also the same thing. The three steps are same. First one encode step. Second one syndrome detection. Third one is what? Using quantum gates. Error correction by using quantum gates. Here phase flip error. That is the reason why we have to consider the phase gate, Z gate. Z gate you have to consider. So see here, first of all, same diagram, the quantum given as alpha ket0 plus beta ket1. In the same bit flip also same state is taken, and ket0 is same, and the diagram control naught is also same, but the only difference is at the output state you have taken H gates, Hadamard gates, because you have to encode na. So that is the reason why you have to put Hadamard gates. So after putting those Hadamard gates, you will get the encoded state as alpha ket plus 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 minus beta ket minus minus minus. Right? So you know how to find these things. So suppose if you have taken 0 here, 0 here. So H of 0 means, we already discussed what H of 0 means, plus. So here also, that is the reason why you are getting here plus. Similarly, H of 0 plus, H of 0 plus. Similarly, if you take 1, then phase change occurs. That is the reason why you will get minus here. So say what happens? Beta minus, get minus, get minus, get minus. Because here 1 is there. That means this C0 gate is activated. This C0 gate is activated. This bit is flipped here. That means 1. This bit is also flipped here. That means 1. Ket 1, ket 1. So whenever H of ket 1 is there, you can write it as ket minus. Here you can write it as ket minus. Here also ket minus. So that is the reason why you are getting alpha ket plus 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 minus beta ket minus minus minus. So first of all, encoding is done. Encoding is done. Second step, syndrome detection. Syndrome detection. For syndrome detection, what you have to do? Additionally, again, Hadamard gates are taken at the input state. 3 Hadamard gates are taken at the input state. Suppose if you have taken X4 also, then another Hadamard gate is have to take. Okay, so there is no need here since 3 bits are given. So see here. So X1, X2, X3, it is given to Hadamard gate, and then it is at the output also given to Hadamard gate. So this one is taken as S1. In the previous diagram also we have taken like this only. Here we have taken as S2. So S1 is, we know, X1 XR X2. X2 is equal to X2 XR X3. So this is the symbol for measurement. Whenever you are measuring, it will shows either 0 or 1. Yesterday we have discussed the classical outputs always either 0 or 1. Right? So superposition state, in the superposition state only you have to write ket 0 or ket 1. Right? Whenever you have measured, it will be that superposition state will be collapsed and it will turns into simple logic 0 0 0 1 1 0 1 1, like that only. So see here, first of all, see X1 X2 X3. So 0 0 0, or in that 0 position you have you will take plus plus plus. You can take plus plus plus. So see here, plus plus plus. So that means 0 0 0 0 0, 1 position. In the first position you have to take minus. Next 0 1 0 0 1 1. Similarly all minuses. That means 1 1 1. Okay, so those X values you need to apply to what? 3 Hadamard gates. See here, 3 Hadamard gates. So H tensor H tensor H. Then after after calculation, you will get whenever H ket plus, you can write it as 0. H ket plus, you can write it as 0. H ket plus, you can write it as 0. Whenever you find ket minus, you can write it as 1. So like this, you have to fill the table. You have to fill the table. Since here all are minuses, so 1 1 1. Okay. Then after S1 S2, S1 S2. So S1 means what? The XR operation between these two. XR operation between these two. XR operation between first 2 bits. 1 0 1 0 1 1 1 1. Since 1 1 is there, 0 0. 1 0 1 0 is there, 1 1. 0 1 is there, 1 1. 0 0 0 0. Now S2. S2 means what? These two. These two. These two. Apply XR operation between these two. Again. Again. So you are getting these values 0 1 1 0 0 1 1 0. Finally, at the end, again you are applying Hadamard gates. Right? So again, after applying Hadamard gates, simple. Since 0 zeros are present, you are getting plus plus plus. Again, plus plus minus. Since here 1 is there. See, where is this thing? Yeah. So since all are zeros, you are getting all are as pluses. Since 0 0 plus plus, here 1 is there. That is the reason why you are getting it as minus. So here 1 is in the middle. So minus, remaining 2 are plus. So likewise for 1 1 1, you will be getting minus minus minus. Okay. So finally, from the table, we have to find which bit is in error state. Which bit is in error state. So see, carefully observe. Similar to previous one only. So first of all, for 0, 0, here also 0, 0. No bit is changed for 0, 0. Yes, for 0, 1. For 0, 1. See here. 0, 1. For 0, 1, 1, 0. That means third bit is changed. Third bit is changed. Right? So here you have to do the error correction by using quantum gates. No? So here you have to use the gate called Z gate. Z gate. In the previous bit flip, you have used X gate in the bit flip. In the phase flip, you have to use Z gate. Z gate. So Z gate in the which position? Third position. Third position for 0, 1. For 0, 0, no error. No error. For 1, 0, for 1, 0, which bit is changed? 1, 0. First bit is changed. First bit is changed. Next, for 1, 1, 1, where another one is there? Yes, here. 1, 1, 0, 1, 0, 1, 0, 1. Which bit is flipped? You need not to place any Z gate. For 0, 1, you have to put Z gate in the third position. For 1, 0, you have to put Z gate in the first position. For 1, 1, you have to put the Z gate in the second position. So see here, the diagram is like this. After measurement, 0, 0, 0, anti-control, 1, control. 1, control. This is anti-control again. 1, 1, control, control. Yeah. For 0, 1, third bit is flipped. Third bit is in error state. That is the reason why in the third bit place, we have taken Z gate. For 1, 0, first bit is in error state. That is the reason why we have taken Z gate. For 1, 1, the error is in second position. That is the reason why in the second position, you have taken the Z gate. Z gate. So these are called quantum gates. By using quantum gates only, you have to do the error corrections. By using the syndrome technique, you have to find the errors. To find the errors, first you have to encode the state which is given initially. Initial state is what? Ket psi is equal to alpha ket 0 plus beta ket 1. After encoding, you are getting it as alpha plus 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 minus beta minus 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 after encoding. Now after syndrome technique, you are getting a table. From the table, you will find the errors. For 0, 0, no error. For 0, 1, suppose third bit is in error state. For 1, 0, first bit is in error state. For 1, 1, second bit is in error state. No. So that is the reason why no error is there. So 0, 0 line is kept empty. So for 0, 1, third bit is in error state. That is the reason why at the position of third bit, you have placed a Z gate, quantum gate. Next, 1, 0, first bit is in error state. So place Z gate in the first position. 1, 1, second bit is in error state. So place Z in the second position. Like that, you have to do the error correction technique. You can also do it on the Algar set. It is very much interesting. You can do it on Algar set. Okay. So third technique. Ma'am, shall I continue this or yeah, till 5, no? Hello. Else I have to start. Shall I continue?
Yes, sir.
Yeah, okay, ma'am. Okay. So till 5, correct, ma'am?
After that also 5 to 6:30 is also your session only, sir.
Yes, madam. I know, madam.
Mm.
VLSA session. Okay.
Sir. Mm.
Yes, madam. Okay. So Steen code, third error correction technique is, it is also the most important thing. Steam code. So it is a more efficient technique. This is also most important technique. Okay, bit flip, phase flip, and Steam code. Most important error detection correction techniques. Surface coding and shore code also important, but these three plays more vital role in the error detection correction technique. Okay, so right. So Steam code offers a more efficient approach to quantum error correction than shore code. That is the reason why I have left the shore code. Okay, so Steam code is more efficient approach than shore code. Here also, first of all, encoding the Steam code. Steam code you have to encode. So for encoding here, it follows the Hamming code technique, that is 743 technique. Some of the faculty may know this technique also. 743. So what the 7 represents, 4 represents, and 3 represents? What are these things? So 4 represents the data bits, the data qubits. The 7 represents the encoded bits. The 3 represents the parity bits. The parity bits are added to the code bit. The code bit or code qubits or data qubit, and then 4 plus 3, 7. You are getting 7 encoded data, 7-bit encoded data. So here, see here. So yeah, let us consider the parity matrix as like this. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. This is the parity matrix. Let us assume. Okay, let us consider the data qubit as 1, 1, 1, 1, 0, 1. This is the data qubit. Data qubits is 4-bit, no? Right. So now code word is 7-bit. 7. How you are getting from 4 to 7 code word? By adding 3 parity bits. So how the parity bits are added, that will be explained later. So for code word, you have the formula called P1, P2, data 1, P3, data 2, data 3, data 4. So this is D1, this is D2, this is D3, this is D4. Okay, so what about P1, P2, P3? These are parity bits. There is a formula for parity bits. So P1 can be represented as D1 XOR D2 XOR D4. So what is the data bit? D1, D2, D3, D4. No? So 1, 1, 0, 1. So parity bit P1 is to D1 XOR D2 XOR D4 1. So what is the answer? 1 XOR 1 0. 0 XOR 1 1. Final output is 1. Right. So P2 D1 1 XOR D3 0 XOR D4 1. So 1 0 1 1 1 0. Next P3 D2 1 XOR D3 0 XOR D4 1. Right. So 1 0 1 1 1 0 1 1 0. So the parity bit is 1 0 0 1 0 0. Now you can say that code word. We have written the formula P1, P2, D1, P3, D2, D3, D4. Correct? 7-bit code word. So parity bit P1, what is P1? 1. P2, 0. D1, 1. P3, 0. D2, 1. D3, 0. D4, 1. So this is the code word. 10101. See here. Code word 10101. So that is the code word. So now you know the parity bit and then code word. Okay, so let us consider here the formula for syndrome. That means error calculation for error detection. The formula is syndrome S is equal to H. That means parity matrix into R transpose. So R is what? Code word. R is what? 7-bit code word. So we got it as 10101. Correct? We have to transpose it. After transposing, you are getting, so that means rows into columns. So 1 0 1 0 1 0 1. Yeah. So multiply these things, these two things, this with this. So you will get 4 2 2 mod 2. You have to take, this is the formula. This is the complete formula. Syndrome is equal to parity matrix into code word transpose of mod 2. Mod 2. So whenever mod 2 means what? Suppose 4 is divided with 2. So 2 times 4, 0. So you have to consider the remainder value. Mod means. Yeah. So mod 2. So after division, after multiplication, you will get 1 plus 1 plus 1 plus 1. That means 4, 2, 2. With mod 2, 4 is divided with 2. You will get the base as 0. 2 is divided with 2. You will get the base as 0. 2 divided with 2. You will get the base as 0. Whenever S is equal to 0, syndrome is equal to 0. That means what? Syndrome represents the error detection. Whenever S is equal to 0, that means there is no error. That means there is no error. Correct? So here we have taken the code word by using the formula without any error. Without any error. Suppose I intentionally put the error in it. Let us see, it will find it or not. Suppose I have taken 1 0 0 0 1 0 1. Okay. So which bit is in error? This bit. In place of 1, I have taken 0. See whether we can find it or not. So multiply these things. 1 plus 1 plus 1, 1, 1 plus 1. So 3, 1, 2. Divide with 2. You will get it as base as 1, 1, again base as 1, 2, base as 0. That means what? 1, 1, 0. So the value is 8421. Sorry, 0, 1, 1. Yeah. 4, 2, 1. In the reverse order, you have to consider. Yeah. 4, 2, 1. That means what? Third bit. 1 plus 1, third. Third bit is in error state. So you go there and check. Since here 0 is present, you have to change the 0 value into 1. In this way, you can find the error. This is called Steam code error detection and correction technique. The major formula is S is equal to H into, H means parity matrix, into R. R means code word, 7-bit code word, transpose of mod 2. Mod 2. Here the main important thing is how you are getting this R value. R value is getting by the combination of parity. P1, P2, D1, P3, D2, D3, D4. So same, P1, you are getting D1 XR, D2 XR, D4. Similarly, P2 is equal to some formula. P3 is also some formula. So those formulas are given here. Yeah, here. D1, D3, D4, D2, D3, D4. Okay. So this is called Steam code error technique. Next. Yeah. Quantum circuit with C0. C0 gate already we have done yesterday with C0 gate, but upside down. It can be taken as C0. You have to consider like this. This is upside down. Control NOT gate. Okay. So see here. If you find the X gate or plus, you can call it as simply NOT gate. If you find like this, you can call it as control NOT gate. If you find like this, we can call it as C NOT gate, upside down gate, upside down gate. Okay. Why? Because always control bit is in top place and the target bit is in bottom place. Should be in bottom place. But here target bit is in top place, control bit is in bottom place. That is the reason why it is called as upside down gates. Okay, so simplify these things. So ket 0, head mart gate, and control NOT gate with upside down. So similarly, you have to solve the circuit. That means you have to come from right side. Start from right side. See here. See, T gate is reversed. That means upside down circuit into Hadmart, tensor product Hadmart, ket 0, tensor product ket 0. Okay, right. Next, C naught. Again, if you calculate this thing, you will get 1 by root 2, 1, 1, 1 minus 1, tensor product. Again, 1 by root 2 is there, or else again 1 by root 2 is there, because Hadamard gate is there. Na? So 1 by root 2, 1, 1, 1 minus 1. 1 by root 2 into 1 by root 2, you can write it as 1 by 2. Okay, next, ket 0, tensor, ket 0. You can write it as ket 0, 0. Ket 0, 0. So ket 0, 0 means 1, 0, 0, 0. So after multiplication, after tensor product, that means 1 multiply with all the gates, all the matrix, with all the matrix. 1, 1, 1 minus 1. 1 with all the matrix. 1, 1, 1 minus 1. 1 with all the matrix. 1, 1, 1 minus 1. Minus 1 with all the matrix. So minus 1, minus 1, minus 1, 1. Correct. Done. So now we have to multiply with C naught gate, control NOT gate with upside down. So this is also 4 by 4 matrix. This is also 4 by 4 matrix. We are using a technique. No. So whenever C naught gate is on left side, then third and fourth rows are interchanged. Whenever C naught is on right side, third and fourth columns are interchanged. Earlier we discussed like this. But what about upside down gate is present on the left side? This time, second and fourth rows are interchanged. Always, whenever C naught gate is present on the left side, you have to interchange rows only. Whenever the C naught gate is present on the right side, then you have to interchange the columns only. Okay, so for C naught gate, whenever the C naught gate is present on the left side, you have to interchange third and fourth rows. Third and fourth rows. Whenever the C naught gate is present on the right side, you have to interchange third and fourth columns. But here, upside down gate is present on the left side. Since it is in left side, you have to change rows only. You have to change rows only. But the number order is changed. Second and fourth rows are interchanged. Whenever C naught is present on the right side, you can say second and fourth columns are interchanged. Okay, so here also see rows now. So 1, 2, 3, 4. Second row 1 minus 1, 1 minus 1 that will appear here. 1 minus 1 minus 1, 1 that will appear in the second position. So see here. Now simply multiply these two things. After multiplication, you will get 1, 1, 1, 1, 1. So that means what? Ket 0, 0, it is present. Ket 0, 1, it is also present. Ket 1, 0, it is also present. Ket 1, 1, it is also present. So that is the reason why 1 by root 2, ket 0, 0 plus ket 0, 1 plus ket 1, 0 plus ket 1, 1. This is the result. Okay, next thing. This will be done easily, very easily, because a narrow line is present here. You can take identity matrix here. Identity matrix here. Start from the, again, right side. Start from the right side. So similar thing. See here. C naught, upside down, H tensor I, 0 tensor 0. Right. So H means 1 by root 2, 1, 1, 1 minus 1. Identity matrix means 1, 0, 0 minus 1. Okay. So similarly, we can continue like this. You will get ket 0, ket 1, 0. Okay. So shall I continue, or can I go to Quizkit? ma'am. So similarly, you can do this. Quantum protocols are also important. There are two types of protocols. One is quantum teleportation. Second one, super dense coding. Super dense coding. Madam, can I explain these things, or shall we move to Qiskit?
After 5, explain Quiskit, sir.
Okay.
That's
Okay.
better.
Okay,
So
madam.
we'll only complete it by within 5 minutes or.
Okay, ma'am. Okay. It will take around 15 minutes, these two protocols. After that, we'll start Qiskit.
Okay, sir.
Done, ma'am. Okay. Quantum teleportation. So quantum protocols are also very much important. So there are two types of quantum protocols, that is quantum teleportation and super dense coding. Super dense coding. So quantum teleportation. So here let us consider the quantum state. Every time we are taking quantum state as alpha ket 0 plus beta plus here plus beta ket 1. Beta ket 1. Yes, at position A, you are having the quantum state as alpha ket 0 plus beta ket 1. You have to transfer this quantum state or quantum information to B state. B state. Just you have to transfer alpha ket 0 plus beta ket 1 to B. Okay. For that, they have given a Bell state. This is a Bell state. Correct? So 0, 0 plus 1, 1. We already done Bell state. So how you are getting Bell states? So we already discussed. So beta 0, 0 is equal to 1 by root 2 ket 0, 0 plus ket 1, 1. So here A, the state A takes the first two qubits. That means 0, 1. 0, 1. It is taken. The remaining two qubits, that is also 0, 1. Those bits are taken by B bit. B state. B state. Okay. So that means A state has one quantum state, second one qubits, ket 0, ket 1. B state, B point has only 0 and 1. Is it clear? So A state contains alpha ket 0 plus beta ket 1 and 0 comma 1. Whereas B state contains only 0 comma 1 only. Now you have, our task is to transfer alpha ket 0 plus beta ket 1 to B node. B node. Right? So for that, you need a circuit. See here. If A wants to transfer the quantum information to B, this is the quantum information, to B. Here Bell state is defined. We know Bell state 1 by root 2 ket 0, 0 plus ket 1, 1. A takes first two qubits, that is 0, 0, 1. B takes second two qubits, 0, 1, 0, 1. Therefore, A contains the original quantum information state and 0, 1 states, 0, 1. B contains only 0, 1, 0, 1. Okay. Now, represent this in quantum circuit. This is the quantum circuit diagram, the most important quantum protocol. Okay. So, first of all, see here. This is given as alpha ket 0 plus beta ket 1 quantum information. You have to transfer this to here. To here. So for that, first of all, you need Bell state. How you are getting the Bell state? You know, Hadamard gate and control X gate. Whenever the input is ket 0, you will get the Bell state as beta 0, 0 is equal to 1 by root 2, 1 by root 2 ket 0, 0 plus ket 1, 1. Okay. So in order to get this, you have to take the quantum circuit this. So here, this is the quantum circuit. The inputs are also ket 0, ket 0. Then you will get the Bell state as 1 by root 2 ket 0, 0 plus ket 1, 1. Ket 1, 1. See here, after that, a control NOT gate is there. Control NOT gate is there. right? So see here. So Bell state, yeah. So this Bell state, since here you are having a single line, narrow line or bare line, so you can consider there is an identity matrix is present here. So now you have to do the parallel operation. These two lines, from these two lines you are getting this one. Now it is in parallel with I. So what you have to do, C naught from left side to right side, sorry, from right side to left side, C naught H transpose I and get 0 0. So from that you are getting Bell state. So Bell state 1 by root 2 get 0 0 plus get 1 1. So here this thing. Now see, alpha get 0 plus beta get 1 and 1 by root 2 beta not beta 0 0 1 by root 2 get 0 0 plus 1 1 are parallel to each other. See here. Sorry, I have written identity matrix because the state is given here, no? So here alpha get 0 plus beta get 1. So in this line, this state is present. From the quantum circuit, you are getting this one. That means this one and this one are in parallel. Whenever two lines are in parallel, you have to consider the tensor product between these two lines. So here also I am taking alpha ket 0 plus beta ket 1 tensor product of 1 by root 2 ket 0 0 plus ket 1 1. So 1 by root 2 I have written in the first position. So alpha 0 0 0. That means alpha 0 0. Alpha 0 1 1. That means 0 1 1. Now beta 1 with 0 0. Beta 1 0 0. Beta 1 with 1 1. Beta 1 1 1. Okay, clear. Now see in the diagram here a control NOT gate is present. Now we are in second location. This is first, right? Control NOT gate is given. So what is the control bit? First bit is control bit. Second bit is target bit. Whenever the control bit is 0, the target bit is transmitted without any flipping. Whenever the control bit is 1, the target bit is flipped. Here 0 is present, then 1 it will come. Here 1 is present, then it shows 0. Correct? So see here. Whenever the first Q bit is 0, then no change in the second. This is the target bit. Second, this is the control bit. This is the control bit. This is the target bit. This is the control bit. This is the target bit. Control bit, target bit. See here. Whenever the control bit is 0, target bit is transmitted to the output. See, no change here. Because the first bit, control bit is 0. That means target bit is transmitted to the output. So no change in the target bit. See here, control bit is 0. Second. The pen has struck. Yeah, okay. Control bit is 0. The target bit, no need to change. So that is the reason why 0, 1, 1, same. See here, control bit is 1. That means target bit has to flip. So control bit is 1. Target bit is flipped to from 0 to 1. From 0 to 1. Here also, since control bit is 1, the target bit is flipped to 0. Is it clear? Second position, second location is also completed. Whenever the control bit is 0, then no change in the target bit. Whenever the control bit is equal to 1, that means the target bit has to be flipped from 0 to 1 or 1 to 0. Okay, so like this. Now see in the diagram, after second position, you have to move to the third location. Here, Hadamard gate is present in the first position. The position where the quantum gates are present is the most important thing here. Right? So first position, Hadamard gates are present. See, Hadamard gate. You know, Hadamard gate, h of ket 0 can be written as 1 by root 2 ket 0 plus ket 1, or simply you can write ket plus. Right? H of 1, this one is 1. Whenever h of 1 is present, h of ket 1 is present, you can write ket 0 minus ket 1. 1 by root 2 into ket 0 minus ket 1. This can also be written as ket minus. Ket minus. See here, now Hadamard gate is present in the first position. Correct? So that is the reason why whenever 0 is present, you have to put plus. Whenever the 1 is present in the first position, you have to put minus. Yeah, see here, first bit, since 0 is there, 1 second, let me rub. Yeah, 0 is there. So that is the reason why whenever 0 you found, you have to put plus here. See, in the first position, you have taken plus. Similarly, here also you will get plus. Here you will get minus. Here you will get minus. So see here things. So plus 0, 0, plus 1, 1. Sorry, 0, no, sorry, minus 1, 0, minus 1, 0, because here 1 is present. So that is the reason why I have replaced the 1 with minus sign. Okay, right. So that is the operation of Hadamard gate. Right. So see here, plus means what? Plus means 1 by root 2 into ket 0 plus ket 1. 1 by root 2 into ket 0 plus ket 1. So carefully observe these things. So you have to consider alpha with two cases. In the first case, you have to put 0. In the second case, you have to put 1. So that is the reason why, suppose if you put 0, alpha ket 0, 0, 0. Now you have to put 1. 1 by root 2 already written here. Now you have to put 1 plus alpha 1, 0, 0. Is it clear? See, next thing. Plus 1, 1. First you have to put 0. Alpha 0, 1, 1 here. Then after you have to put 1. Alpha 1, 1, 1 here. Similarly for beta also. Beta 0, 1, 0. Now minus. For beta, you have to put minus sign. Here minus sign is there, no? Right. So minus, now 1. 1, 1, 0. Plus 0, 0, 1 minus 1, 0, 1. I think this step is clear. This is the most important and difficult step to understand. I think it is clear. Yes. Please respond. Yes. If you understand this step, then the next step is very much easy. That is the final step only. Yes. Yes, yes. Shall I continue?
Please continue, sir. Continue to the last step.
Okay, ma'am. So now you have to take the common as alpha, ket 0, 0, 0, 0. I have taken 0, 0 as common. Then what left here? Alpha ket 0 is left here. So alpha ket 0. Since 0, 0 is taken as common, where you can find 0, 0? No. Here. 0, 0 is there. That means plus beta ket 1. See here. Beta ket 1. Now take 0, 1 as common. 0, 1 as common. So 0, 1. So here 0, 1 is present. So where you can find 0, 1? Here 0, 1 is there. So that means alpha ket 1 plus beta ket 0. Next, 1, 0 is taken as common. Alpha 1, 0 is taken as common. So alpha ket 0, 1, 0, 1, 0 here. Minus beta ket 1. This one. Next, take 1, 1 as common. Alpha ket 1, 1 1 here minus beta ket 0 minus beta ket 0, right? So what we are doing here, we are transferring alpha ket 0 plus beta ket 1 from A source node to destination node B. So finally you will get, you have to get alpha ket 0 plus beta ket 1 at destination point B. Okay, so for that, suppose 0 0 0 0 is taken as common, so then you are getting this one, present state. Yes, so this state is transferred to B. So correct, alpha ket 0 plus beta ket 1. Now this one is multiplied with identity matrix. Even though if it is multiplied with identity matrix, you will get that the same thing, alpha ket 0 plus beta ket 1. This is at B. Okay, next for 0 1, for 0 1 you are getting alpha ket 1 plus beta ket 0, alpha ket 1 plus beta ket 0, right? So for that, see here, in place of 0 you are finding 1, you are getting 1. In place of 1 you are getting 0. That means the bits are flipped. Whenever the bits are flipped, you are using the gate called X gate. Correct? In the bit flip error detection technique, we used X gate. No, in the phase detection technique, we are using Z gate. So for that, we need to give this quantum state to X gate. So X gate, what it will do? It will flip 1 to 0, 0 to 1. So hence you will get alpha ket 0 plus beta ket 1. Similarly, for 1 0, this is the equation, alpha ket 0 minus beta ket 1. So for that, alpha ket 0 minus beta ket 1. So for that, for whenever you find 1, the phase change you may observe. Phase change you may observe. So that is the reason why I have taken the quantum gate Z. So Z alpha ket 0, the minus can be changed to plus beta ket 1 because of this phase gate, Z gate. Now see here, for 1 1, you are getting alpha ket 1 minus beta ket 0, minus beta ket 0. Now see, you have to change 1 to 0, 0 to 1, and then you have to convert this minus value to plus value. That means you have to use two gates. For flipping, for bit flipping, you have to use Z gate. For phase flipping, you have to use Z gate. Those two gates are used here. Then you can get alpha ket 0 plus beta ket 1. So from B, at B, you are getting the value, you are getting the state, quantum state, which is transferred from A. That is alpha ket 0 plus beta ket 1. You are getting the same value. Whatever the value at A is transferred, that value is received at the point B. Okay. So this is called quantum teleportation. So here I have simplified the things. Okay. Next, super dense coding. Second one is super dense coding, right? It is exactly reverse
sir.
operation. Madam.
Sir, can we take 10 minutes break, sir? Because you are
Sure.
continuously telling, no? Please take
Okay.
10 minutes break and join, sir.
Sure, ma'am. Thank you. Thank you very much.
Yes. Participants, please stay online. Sir will join very soon.
x I into beta 0 0. Beta 0 0. Clear. So after completion of first part, this is the first part. Now you have entered into the second part. First part is finished. Second part. See, second part. So control X is there. That means C naught. After that, head mod operation need to perform. So see here. First, 1 by root 2 get 0 0 plus get 1 1 plus get 1 1. So it is given to C naught. C naught gate. What it will do? Whenever the first bit is 0, it will transfer the second bit without any change. Whenever the first bit is, that is control bit is 1, it will flip the target bit. If it is 1 is there, then it will change it as 0. 0 is there, it will change it as 1. So see here, first bit is 0. So it won't change the second bit. So 0 0. CX means control not gate. Next, since the first bit is 1, it will flip the bit here. So 1 is there, that means it will flip to 0. It will flip to 0. So after that, 1 by root 2 get 0 0 plus get 1 0. Till now, till this point, we have completed. After that, we have to apply head mod gate. Head mod gate. To apply head mod gate, you can take the common, get 0 as common. Yes, get 0 as common. So if you take the get 0 as common, what you will get? 1 by root 2 get 0 plus get 1. Get 1. Get 0. If you take get 0, right? Common. And then after, see here, identity matrix is there. Identity matrix is there. So H tensor product I. So H is applied to this gate, sorry, this matrix complete state, and then I is applied to this one. So whenever you know H of ket 0 is equal to, you know, the formula 1 by root 2 ket 0 plus ket 1. So we can simply write it as ket 0, ket 0, correct? So for this entire thing, we can write ket 0. Now, identity matrix into ket 0, we can write it as ket 0. The tensor product between ket 0 and ket 0 can be taken as 0, 0. So that is what we get, 0, 0. So similarly, for the remaining also, we will get 0, 1 for 1, 0, 1, 1. First, we need to apply control X gate and then take common. Here, we can take common as 1. Then after, we have to apply H transpose, sorry, H tensor I. H is applied to this one and I is applied to this one. So after applying H head mod value to this, we can get 0. After applying I to this value, we can get 1. So 0, 1, 1, 0, 1, 1. In this way, we can transmit the classical output, classical values to the output state. Yes. Is anyone having any doubts? Then I will go to Quiskit. Please let me know quickly. Super dense coding and quantum teleportation or quantum error correction. Please let me know quickly. Or else I can go for Quiskit. Time permits, no, and then I will go for quantum algorithms also. Jewish algorithm, Jewish Josja algorithm, and Grover-Sachs algorithm. Then Simon's algorithm is there. Then yeah, no cloning theorem is there. Yeah. So please, if anyone is having any doubt, then let me know. Otherwise, I can go for Quiskit. Yes.
Participants, if you have any queries, the forum is open for you. Please raise your queries. And you can post your queries in the chat box also.
Ma'am, shall I continue with Qiskit?
Please, yes, sir. Please continue, sir.
Right. Thank you. So first of all, we need to install Python programming language. Yesterday we discussed it should be above 3.9 version, and then after installation of Python 3.9 version, you have to install furthermore. I will send the details to Madam Coordinator. So the installation process and all. After that, you have to open an account. In that, so you have to type Conda activate Qiskit environment _env. Then press enter. You will go into the Qiskit environment. Then open Jupyter Notebook. Jupyter Notebook. Okay. Yeah. So I already done the programs. I will explain each and everything step by step. So see here. Yeah. So first of all, we discussed what is ket0, what is ket1. So ket0 and ket1 are called column vectors. Column vectors. Ket0 means 1, 0. Ket1 means 0, 1. So how to write the ket values? So normal in Python, you can write, normal Python, you can write import numpy as np and import simpy as sp. Simpy means symbolic tool, simpy. Okay, so as sp, and ket0 is equal to np dot array of 1 comma 0. So you print ket0. If you print ket0, it shows like this. So see here, after run, you can show like this 1 0, but it is not in the proper format. So I need the column vector like this, like this. So for that, what I have to do, so because that reason only I have imported simpy as sp. So similarly import numpy as np, import simpy as sp, ket0 is equal to np dot array of similar thing. And then this is the most important step, sp dot matrix. It shows in the matrix format, sp dot matrix of ket0. Then you can run it. So you can show, you can see 1 0, ket1 0. So similarly for ket1, you will get 0 1, 0 1. See here. Now import numpy as np and import simpy as sp. Control not gate. I have taken control not gate. So that is equal to np dot. You have to type everything because I have done some problems based on ccx. So that is the reason why I have typed everything. Okay. So how you get ccx control not gate? That is also called as Toffoli gate. Toffoli gate. In Toffoli gate, what you will do? The 6th and 7th columns are interchanged. So see here, this is the first column, second, third, fourth, fifth, sixth, seventh. Sorry, 0, 1, 2, 3, 4, 5, 6, 7. Correct? So sixth and seventh rows, sorry, seventh columns are interchanged. 1 second. Columns are interchanged. See here, 1 is present here. Actually, 1 should be here. Correct? 1 is present in the sixth column. Sixth column, but it should present here. That means sixth column and seventh columns are interchanged in CCX. Okay. So SP dot matrix of CCX. Then you will get the equation like this. Okay. So after that, see here. Tensor product, how we can calculate the tensor product? Mathematically we can know, manually we can calculate, like suppose 1001 is there, so tensor product with another 1001 means what? 1 into the entire matrix, 0 into the entire matrix, again 1 into the entire matrix, 0 into the entire matrix, like that we have to do. But here just a simple formula called cron np dot cron of np dot cron ket 0 comma ket 0. Actually, if suppose only ket 00 is there, not triple zero, just double zero, ket 00 is there, then no need of placing np dot cron here, and no need of placing again ket 0, because you are having 3 bits. That is the reason why we have to consider 2 times np dot cron of ket 0 comma ket 0 comma ket 0. Then it will do first ket 0 tensor product with ket 0. After getting the answer, the answer is again tensor producted with ket 0. So sp dot matrix of ket 0 0. So ket 0 0 means what? 1, remaining all zeros. Suppose if you are getting 0 0 1, then you will get 0 1, remaining all zeros, right? If you get triple 1, then all are zeros except the last one, it will be 1. Okay, so tensor product can be calculated like the formula called cron, kron, chroniker. Okay, similarly here also 100. So np dot cron of ket1 comma ket0. First it will do the tensor product between ket1 comma ket0, and then after getting the result will be again tensor producted with ket0. So the final product is stored in ket100. So that will be represented like in the matrix format. So sp dot matrix of ket100. So ket100 means what? So what is this value? 4. So S4 0 1 2 3 4. At the fourth position you will get 1. Remaining all the places you will get it as 0 0. So run this. Yeah, you will get that one. Similarly, CCX ket 00. What is this? At the rate. At the rate is used to multiplication purpose. CCX, it is an 8-bit, 8 by 8 matrix. This is CCX, 8 by 8 matrix. Now you have to multiply this with ket 00. Ket 00 means, so this one, 1, remaining all zeros. So that is 8 by 1 matrix. 8 by 8 matrix is multiplied with 8 by 1 matrix. So for multiplication, you need to consider the at the rate symbol. At the rate symbol. Okay. So then you will get like this. This is the equation. So see, after run, second, what is this? 1 second. It is getting error. So, okay. Yeah, CCX get underscore 000. 0, 0 is not defined. We have defined, no? Yeah, we are getting the answer. So CCX at the rate, that means multiplication with 0, 0, 0. So we are getting 1, remaining all zeros. You can manually multiply and then check the results also. So see here, I is given as 1001, x is equal to 0110. This is the value of x. Later we will see why you are getting x as 0110. How you can get 0110. So all we can see. So x is equal to 0110. Again, I is equal to 1001. So cube is equal to. So that means here the circuit diagram is like this. So I will draw the circuit diagram. So given I, then after x, then after I, like that he is given. 1 second. Yeah. So I, x, I. So you have to calculate Q. Q means what? Result. Q means result. So Q. So what is the Q value? I tensor product X tensor product I. So how you can write np dot cron of np dot cron of I comma X comma what? I comma I. So like that bracket. So this is the way. See here. So np dot cron of np dot cron of I comma x comma I. So first of all, it will do I x, the tensor product, and then the result will be tensor producted with I, and then finally sp dot matrix of q. So it will be shown in the matrix format. It will be shown in the matrix format. You can run this. Yes. See, again, the equation is like this, and the circuit is like this. I is equal to given as 1001, x is given, q1 is given, q2 is given, and q3 is given. So see here, I, x, and then q1. Okay. The diagram is like this, I think. I, x, then q1, yeah, q2 ccx. Okay, here q1, next ccx, control x. So that is represented as q2. Finally q3. So q3 is equal to what? So q3 is equal to q1. Q1 means what? I and again x are in parallel. So I and x are in parallel. So that is q3. So see here, q1 is similar to q3. Q1 is similar to Q3. That is the reason why Q3 is equal to Q1. They simply written like this. Okay. This is the circuit diagram. So first you have to calculate Q1. How you can calculate Q1? I tensor product X tensor product I. Because it is a straight line. You have to consider I. So after calculating I1, and then you have to calculate CCX. That is Q2. Again, after calculating Q2, you have to calculate Q3. Since Q1 and Q3 are same, no need to calculate again. Now, you have to multiply these three. Q1 at the rate Q2 at the rate Q3. So see, that is the circuit. We have to calculate like this. See here, Q3 is equal to Q1. So SP dot matrix of Q3 at the rate Q1, sorry, Q2 at the rate Q1. Yeah. Next, like this you can get. And then see here, state vector. This is called actually ket0. Ket0 can also be called as state vector. Ket1 is called as state vector. Ket00 is called as state vectors. Okay, 0, 1, 1, 0. Everything in the form of ket or bra can be represented as state vectors. Okay, so to get ket0, the way is import numpy as np from Qiskit, import from Qiskit, import quantum circuit from Qiskit dot quantum underscore info, import state vector. From Qiskit, you have to import state vector. So ket0 is equal to, earlier we have written like this, np dot array of suppose ket0 key 1 0, like that we have written. But here, whenever you consider state vector, you can simply write ket0 is equal to state vector of simply in the form of 1 comma 0 in the square brackets. 1 comma 0. Okay. Ket0 dot draw in the brackets, you have to write latex. Then it will show the state vector as ket0. State vector as ket0. Okay. Similarly, ket1. Ket1 means what? Ket1 is equal to state vector of 0, 1. Ket0, 1, 0. Ket1, 0, 1. So within the brackets, you have to write latex. So that then only it will show the ket1 in the format, in this format only. So ket1. Similarly, from Qiskit, import, see here. Now you are
Sir, unmute yourself, sir.
Sir Ashraf sir, please unmute yourself.
okay. Okay, man. I don't know how it is getting muted. No, okay.
Yes, sir. It is okay now.
Yes. Okay, ma'am. Thank you. Yeah. So what is the value of x? Yesterday we discussed the value of x means 0, 1, 1, 0. So to get 0, 1, 1, 0, the simple technique is it is called as operator. Sorry, operator. So see here, first of all, from Qiskit, import quantum circuit. These steps are common for everything. Every quantum circuit, these steps are common. From Qiskit dot quantum underscore info, import operator. So QC is equal to, QC means quantum circuit, is equal to quantum circuit of 1. 1 means 1 qubit only. We are considering only 1 qubit. Okay. So QC dot x of 0. That means what? 0 means what? The first line. The first line is 0th line. After that, another line is drawn. That is called second line. Second line means 1. third line means 2. Okay, like that. So you have to consider only 1 qubit. That is the reason why you have taken 1. So in that qubit line, you have taken x gate. So see here, 1 second. I will show it to you. You have considered only 1 line. Okay, so that line is 0th line. 0th line. If you consider another line, that becomes 1. Another line, that becomes 2. Okay, so here only 1 line is considered, because in the quantum QC is equal to, they have written QC dot quantum circuit. QC is equal to quantum circuit of 1. That means only 1 qubit is considered. So no need to take these 2 lines. In that they have considered X gate. That is the meaning of this line. That is the meaning of this line. Okay, QC dot X of 0. Now what is the X? What is the value of X? So X is equal to operator on QC. Operator on QC. So X dot draw of latex is equal to, see here, this is the matrix equation, matrix formula for X gate 0 1 1 0. Similarly for Y, same thing. I have written all the things are as same here, but in place of X, I have considered Y gate. So to get the Y gate matrix, so see here, 0 minus I 0. Just the operator is the keyword here, operator. Next, for Z gate, similarly, now I replaced Y gate with Z gate. So then you can get the value of Z gate as 1 0 0 minus 1. This is the value of Z gate. Sir, where from you are getting these values? Qiskit is giving. So from manually, how we can get the X value as 0 1 1 0, Y value as 0 minus I 0, Z value as 1 0 0 minus 1. So all these values are derived from the block sphere. Okay, so there is no time to explain the block sphere. There is a lengthy, at least 5 to 6 pages derivation is there. If you need, I will forward to you. So from that derivation, you will get the gate called X gate, Y gate, Z gate, and all, Hadamard gate and all. Okay. Similarly, for H gate, if you replace Z with H, you can get, see here, 1 by root 2. If you take it as common, 1 by root 2, 1 1 1 minus 1. Right. Similarly from Qiskit, now S gate means 1 0 0 I. T gate, S gate means what? 1 0 0 e power I theta. That is called phase gates. Phase gates are of 2 types, S gate and T gate. S gate is when we can get S gate, in place of theta, you have to put pi by 2, 90 degrees. Then you can get 1 0 0 I. In place of pi, if you in place of theta, if you write pi by 4, then you will get 1 0 0 1 by root 2 plus I into 1 by root 2. I into 1 by root 2. See here. So this is T gate. So these gates are very much important. Without these gates, you cannot construct a quantum circuit. Yes, right. So similarly, there is another way to get ket 0 value. See here, ket 0 is equal to state vector. Earlier we have written state vector of in the square brackets 1 0, like that. Ket 0 dot draw latex. Then you will get this value. But here you can also write ket 0 is equal to state vector dot from underscore label of 0, just 0. Then you will get ket 0. Suppose if you apply this ket 0 value to X gate, we know X gate is also called as NOT gate. If the input is 0, then the output will be 1. So how you are getting x is equal to, if input x is equal, sorry, input is equal to 0, then output is output as 1. Yesterday we have discussed by using outer product form, but here we need not to do everything manually. The simple formula is evolve. So get 0 dot evolve of x. That means we are applying get 0 to x gate. Dot draw latex. Then you will get, see here, then you will get 1. So if you apply 0 to x gate, then you will get as 1 output. Similarly, if you apply 0 to y gate, then you will get it as I get 1. Okay, next. From Qiskit, import, similarly, ket1. So ket1 here. So this ket1 value is applied to y gate. So if you want to show me, then I can show the previous slides, yesterday's slide. So is it correct or not? You can check there. So ket1 evolve of y. So ket1 is applied to y gate, then you can get minus I ket 0. Right? Similarly, you are applied ket 0 to z gate, then you can get as ket 0. If you apply 1 to z gate, then phase change occurs. That is minus 1. So 1 is applied to z gate, then you will get minus ket 1. 1 second. You have to run all the things. Yeah. So again, 0. Ket 0. It is applied to Hadamard gate. So what it will get? When h of ket 0 is given, then 1 by root 2 ket 0 plus ket 1. Correct? So 1 by root 2 can be written as root 2 by 2 ket 0 plus root 2 by 2 ket 1. Anything is fine. Next. Again, ket 1 is applied to h gate. Ket 1 is applied to h gate. Then you will get minus 1 by root 2 ket 0 minus ket 1. If you apply 0 to Hadamard gate, then you will get plus. If you apply 1 to Hadamard gate, then you will get minus sign. Okay, so run this also. Right. Next, again 0. It is applied to S gate. After applying S gate, you will get ket 0. Now apply 1 to S gate. You will get it as I into ket 1. Second. Yeah. So I into ket 1. Now, similarly, if you apply ket 0 to what? Apply ket 0 to T gate. Then 0 will be getting. Similarly, 1 is applied to T gate. Then this is the answer. You can solve on your own. After that, you can check on the Jupyter notebook. So how to construct a simple quantum circuit? So from Qiskit, 1 second, I have to run all the things. Yes. From Qiskit, import quantum circuit. The step is common. QC, quantum circuit is equal to quantum circuit of 1, 1. First one represents the qubit. Second one represents the classical bit. Here you have considered 1 qubit and 1 classical bit. right? So QC dot headmart gate, you are taking headmart gate, you can take X gate, S gate, T gate, Z gate, Y gate, whatever you can take. So H of 0, that means at 0th position, you are taking H gate. QC dot measure 0, 0. First 0 represents the measurement of qubit value is stored in classical 0. That is the meaning of 0, 0. The measured value of qubit is stored in the classical bit 0. Classical bit 0. After measurement, there is no superposition state. All the states are classical states only, right? So after measurement, the value is stored in classical bit 0. So QC dot draw of MPL, matplotlib, MPL means. So you will get the diagram like this. This is the diagram for measurement. Yes. Yeah. Now the important part, it is simulation. How you will simulate the quantum circuit. So here you have two types of simulators. One is basic simulator, second one air simulator, AER, air simulator. So from Qiskit dot providers dot basic underscore provider import basic simulator. Next, simulator is equal to basic simulator. Next, what is the job? Job is to simulate. You have to run the quantum circuit. How many times you have to run the quantum circuit? 100 times. It is your wish. 100 or 500 or 300 or 1000, whatever value you can take, you can take. Okay. So job is equal to simulator dot run QC comma shots is equal to 100. So result is equal to job dot result. And that means the result value, the value you are getting from job is stored in result, and then finally counts is equal to result dot get underscore counts. So print counts. Then you will get like this. See here. So 1 after 100 iterations, after 100 times it will be iterated. The probability of getting 1 is 46 times. The probability of getting 0 is 54 times. So those values represents the probability values. Similarly, now you have considered two gates. So those two gates are represented in 0th line only. That is the reason why I have put here 0, H of 0, X of 0. If you put H of 0, X of 1, then H will be here and X will be here and X will be here only. Okay. So now these two are in the same line. Again, measure. Since you have written measure, so measure symbol is here. Okay. So this is the way to draw the diagram. And then here we have used two types of simulators. So basic simulator and air simulator, AER, air simulator. So the same steps what we have followed in the earlier step, the same thing here also you have to follow. Sim underscore basic, that is the name I had given. Sim underscore basic, sim underscore AER. Both are simulators only. Basic simulator, this is air simulator. Next, counts underscore basic, counts underscore air is equal to simulator underscore basic dot run, simulator underscore air dot run. Quantum circuit, on quantum circuit, shots is equal to 100, and then after results, and then counts. So print counts underscore basic, print counts underscore air. So this is the values you will get. Every time it values, for every iteration, the values may be changed. So 1 for 48 times, 0, 52. So for basic simulator, for air simulator, 150, 0, 50 times. So if you want to visualize the things, you can visualize from Qiskit dot visualization, import plot underscore histogram, plot histogram of count underscore air. So I have written for air. So 50-50 na. So it will show the same way 50-50 because Here we are getting 50-50. Suppose if you run again, the value may be changed 51-49. So now run this. You will get 59, 51-49. Yeah, like this you will get. Similarly, for this one also, basic simulator. Yeah. And how much time left?
10 minutes, sir.
10 minutes only. Can I stop here for any doubts? Or else, yeah. Is anyone having any doubts? Why? Because it not explain the block spheres, no? So that is the reason why I stopped here. So these are called block spheres. So Polis X gate, Y gate, Z gate are having angle called 180 degrees phase shift. Polis X, Y, Z gates. S gate, T gates are with 45 degrees. So that will be, first we have to explain theoretically, then only you will be understood. These are all called Q sphere, Q spheres. Block spheres, first you have to know. After that, you have to know about Q spheres. In block sphere, you will represent only one qubit. In Q sphere, see here, either you will represent ket 0 or ket 1. But in Q sphere, you will represent ket 0, 1 at the same time. See here, ket 0, 0, ket 1, 1. You can represent both the values at the same time. Yes. Sir Abdul sir, sure, madam will send the entire things to you. Please ask me any doubts if you have. In today's
Participants, if
session.
you have any queries, you can raise the queries now, or else you can post it in the chat box also.
All are clear.
Roja madam,
Yes, ma'am.
yeah, please give the closing.
Yeah. Good evening, everyone. This sessions of Dr. Ashfali sir. Sir has clearly explained what are the types of quantum error detection and correction techniques. All the three detailed with clear examples, and also sir has clearly made us understand what is this Quizbit and how we can generate block space and QB with Quizbit using simulation software. Thank you so much for your explanation. In future, we are expecting from it, sir, like these sessions.
Thank you.
Thank you so much, sir. Participants, you can write the exam in your
Thank you, sir.
FDP portal. You can log in with your credentials and please kindly submit your feedback as well as complete your examination in between 6:30 to 7:30.
Madam, can I leave?
Yes, sir.
Thank you, madam. Thank you very much. Vishnu Priya,
Thank you so
madam.
much, sir.
Mehta, madam. Thank you. Thank you very much.
Participants, if you can leave now and please join the validatory session by 7 p.m. Thank you.